For most of human history, we had it all figured out. Or at least, we thought we did. Space and time were simple. They were obvious. They were separate. Space was where things happened. It was the stage, the arena, the container of the universe. You could move through it, left, right, up, down, forward, backward, 3 dimensions of pure empty nothingness waiting to be filled with matter. And time? Time was different. Time was the clock ticking in the background. It moved forward, always forward, 1 second after another, completely independent of anything happening in space. You could move through space however you wanted, but time just marched on at its steady, unchanging pace. This wasn't just common sense. This was reality, as every single person experienced it, every single day. The ancient Greeks thought this way. Medieval scholars thought this way. Your ancestors thought this way. You probably still think this way when you're going about your daily life. Because honestly, why wouldn't you? Space was geometry. Time was duration. They were as fundamentally different as hot and cold, as matter and energy, as existence and nothingness itself. The idea that they could be related, that they could be unified, that they could be different aspects of the same thing would have seemed as absurd as suggesting that up and down was somehow the same direction. Philosophers debated the nature of space for centuries. Is it real or just a concept? Does empty space actually exist, or is it defined only by the objects within it? And they debated time too. Does it flow? Is the future already determined? Does the past still exist somewhere? But nobody, and I mean nobody, thought to ask whether space and time might be connected to each other. That question didn't even make sense. It was like asking whether the color blue is connected to the number 7. This separation seemed so obvious, so fundamental, so undeniably true, that it formed the bedrock of all physics, all science, all human understanding of the universe. We built our entire scientific worldview on this foundation. And we were completely wrong. Isaac Newton didn't just accept the separation of space and time. He formalized it. He mathematized it. He turned it into the foundation of his entire system of physics. And that system worked so incredibly well that it seemed to prove beyond any doubt that space and time were exactly what everyone always thought they were. Newton introduced the concept of absolute space. Picture an infinite, 3-dimensional grid stretching out in every direction forever. This grid exists whether there's anything in it or not. It's not made of anything. It doesn't depend on matter or energy. It just is. It's the reference frame for all motion, the fixed background against which everything moves. This absolute space has a specific property. It's the same everywhere and for everyone. It doesn't matter where you are in the universe, you're standing in the same absolute space. It doesn't change. It doesn't warp or bend or flow. It's like an eternal, unchanging coordinate system that God Himself set up at the beginning of time and will exist unchanged until the end of time. And speaking of time, Newton gave us absolute time too. Time, according to Newton, flows uniformly everywhere in the universe, completely independent of anything that happens within it. There's a cosmic clock ticking away, and it ticks at exactly the same rate whether you're on Earth, on Jupiter, or in the furthest galaxy imaginable. 1 second here is exactly 1 second there, always, without exception. This absolute time means there's a universal now that spans the entire universe. When you say right now, at this very moment, there's a definite answer to what's happening everywhere in the universe at that exact same instant. Events can be ordered absolutely. This happened before that happened after this, and everyone in the universe would agree on that ordering. Newton's framework gave us a clockwork universe. Everything moves through this absolute space according to precise mathematical laws, with absolute time ticking away in the background, the same for everyone, everywhere. And it worked. My God, it worked beautifully. Newton's laws predicted planetary motion. They explained falling objects, pendulums, projectiles. They let us calculate the paths of comets, the tides of the ocean, the behavior of springs and pulleys, and every mechanical device we could dream up. For over 200 years, this framework dominated physics. It was tested again and again and kept passing every test. Scientists used it to make predictions that came true with stunning accuracy. Engineers used it to build machines that actually worked. Astronomers used it to discover new planets before anyone had seen them, just by calculating where they should be based on Newton's laws. The framework was so successful, so powerful, so seemingly correct, that by the late 1800s, many physicists thought the fundamental laws of the universe were essentially complete. Sure, there were a few small puzzles left to clean up, a few decimal places to refine, but the big picture was done. We understood how the universe worked. Absolute space, absolute time, clear separation between the two. Everything moving according to deterministic laws through this fixed framework. Reality was a machine, and we had the instruction manual. And then everything fell apart. In the late 1800s, physicists were confident, really confident. They had Newton's laws, they had Maxwell's equations describing light and electromagnetism, and together these seemed to explain just about everything. But there was this one little detail that bothered some people. If light is a wave, what exactly is waving? Sound waves travel through air. Ocean waves travel through water. Earthquake waves travel through rock. Every wave humanity had ever encountered needed a medium, a substance, to do the waving. So what was the medium for light waves? Scientists came up with an answer: the luminiferous ether. This was supposed to be an invisible, massless substance that filled all of space. Light waves were vibrations in this ether, rippling through it the way sound ripples through air. The ether had to be everywhere, in the space between stars, between planets, even in what we call empty space. It had to be rigid enough to support the incredibly fast vibrations of light waves, yet offer no resistance to planets moving through it. Now, if the ether existed and filled all of space, then Earth must be moving through it as we orbit the Sun. We're traveling at about 30 kilometers per second in our orbit, so we should be plowing through this cosmic ether like a ship moving through water. And if we're moving through the ether, then we should be able to detect that motion. Enter Albert Michelson and Edward Morley. In 1887, they set up what should have been a simple experiment. They built an incredibly precise device called an interferometer that could detect tiny differences in the speed of light traveling in different directions. The logic was straightforward. If Earth is moving through the ether, then light traveling in the direction of Earth's motion should have a different speed than light traveling perpendicular to that motion, just like how a boat moves faster downstream than it does across the current. They expected to measure Earth's speed through the ether. They expected to detect the ether wind as our planet plowed through this cosmic medium. They ran the experiment. They checked their equipment. They ran it again at different times of day, different times of year, when Earth was moving in different directions. And they found nothing, absolutely nothing. No matter which direction they measured, no matter when they measured, light always traveled at exactly the same speed. There was no difference at all. It was as if the ether wind didn't exist, as if Earth wasn't moving through any medium at all. This wasn't a small discrepancy. This wasn't a measurement slightly off from the predicted value. This was a complete null result. The effect they were looking for should have been easily detectable with their equipment, but it simply wasn't there. At first, people thought maybe they'd made a mistake. Maybe the equipment wasn't sensitive enough. Maybe they'd overlooked something. But the experiment was repeated, refined, improved. Different scientists tried it in different ways. The result was always the same: nothing. No ether wind, no variation in the speed of light. The physics community was baffled. Some tried to explain it away. Maybe Earth drags the ether along with it? But that created other problems and contradicted other observations. Maybe the ether doesn't exist at all. But then what is light waving in? How can you have a wave with nothing to do the waving? For nearly 2 decades, this result sat there like a thorn in the side of physics. It was the anomaly that didn't fit, the observation that made no sense in the established framework. Most physicists just kind of ignored it, or hoped someone would eventually figure out a way to explain it within the existing theory. But this wasn't just a minor puzzle. This was a crack in the foundation, and that crack was about to bring down the entire edifice of absolute space and absolute time. The Michelson-Morley result was strange, but it got stranger, because it wasn't just one weird experiment. As scientists studied light more carefully, they kept finding the same bizarre pattern over and over again. The speed of light never changed. No matter what you did, no matter how you measured it, light always traveled at the same speed. And this violated everything we understood about motion. Think about how normal velocities work. You're on a train moving at 50 kilometers per hour. You throw a ball forward at 20 kilometers per hour relative to the train. To someone standing on the ground watching, that ball is moving at 70 kilometers per hour. You add the velocities. This is so obvious, so fundamental to our everyday experience, that it seems like it couldn't possibly be wrong. Now apply that same logic to light. You're on a spaceship moving at half the speed of light, and you shine a flashlight forward. The light leaves the flashlight at the speed of light relative to you. So, to someone watching from a stationary planet, the light from your flashlight should be moving at 1.5 times the speed of light, right? Just add the velocities like we did with the ball. Wrong. Dead wrong. The light is still moving at exactly the speed of light. Not 1.5 times the speed of light. Just the speed of light. The same speed it would be if your spaceship was standing still. This makes no sense. It violates the addition of velocities. It seems to break basic arithmetic. If you're moving forward and you shine light forward, how can that light not be moving faster than if you were standing still? But experiment after experiment confirmed it. Light from a moving source travels at the same speed as light from a stationary source. Always, without exception. Whether the source is moving toward you, away from you, or standing still, the light from it reaches you at exactly the same speed, approximately 300,000 kilometers per second. And it's not just about the source. The observer's motion doesn't matter either. If you're moving toward a light source, the light doesn't approach you any faster. If you're moving away from a light source, the light doesn't approach you any slower. The light always reaches you at the same speed. This is completely unlike anything else in physics. If you're in a car driving toward another car, your relative velocity is the sum of both speeds. If you're both driving in the same direction, your relative velocity is the difference. This works for cars, trains, planes, bullets, sound waves, water waves, literally everything we'd ever measured. Everything except light. Some physicists tried to patch up the old framework. Maybe there was something special about the equations for light. Maybe there was a preferred reference frame after all, even if we couldn't detect it. But every attempt to preserve the old world view, while explaining this constant speed of light, ended up creating more problems than it solved. The speed of light was presenting us with a fundamental paradox. In Newton's framework, with absolute space and absolute time, velocities had to add. There was no way around it. If something is moving at velocity a and something else at velocity b, their relative velocity is a plus or minus b depending on direction. This is mathematics. This is logic. This is how a universe with absolute space and absolute time has to work. But light didn't follow these rules. Light was doing something else entirely. And if light wasn't following the rules, then maybe the rules were wrong. This wasn't just a puzzle about light. This was a crisis in our understanding of reality. Because if velocities don't add the way we thought they did, if the speed of light really is constant for all observers no matter how they're moving, then something deep and fundamental in our picture of the universe has to be wrong. Either our experiments were all systematically flawed in exactly the same way, which seemed increasingly unlikely as more evidence piled up, or our basic understanding of space-time and motion was fundamentally broken. Most physicists in the late 1800s and early 1900s were still trying to save the old framework. They were trying to explain away the observations, to find some clever interpretation that would preserve absolute space and absolute time, while accounting for this weird behavior of light. One person decided to do the opposite. Instead of trying to save the old framework, he asked, what if we take these observations seriously? What if the speed of light really is constant, and everything else we think we know has to change? That person was Albert Einstein. In 1905, Albert Einstein was 26 years old and working as a patent clerk in Switzerland. He wasn't a professor. He didn't have a research lab. He was just a guy evaluating patent applications during the day and thinking about physics in his spare time. And in that year, he published a paper that would completely revolutionize our understanding of reality. The paper was titled On the Electrodynamics of Moving Bodies, which sounds almost boring, doesn't it? But in that paper, Einstein did something radical. He didn't try to explain away the constant speed of light. He didn't try to patch up the old framework. Instead, he started with two simple postulates and followed them to their logical conclusions, no matter how strange those conclusions became. The first postulate was the principle of relativity. The laws of physics are the same in all inertial reference frames. If you're in a windowless room, there's no experiment you can do to tell whether you're sitting still or moving at a constant velocity. This wasn't new. Galileo had proposed something similar centuries earlier, and it fit fine with Newton's framework. The second postulate was the radical one. The speed of light is constant for all observers, regardless of their motion or the motion of the light source. Einstein didn't try to explain this. He didn't try to derive it from something else. He just took it as a fundamental fact of nature, as confirmed by every experiment that had tried to measure it. And then he asked, if these two things are true, what else must be true? Most physicists at the time thought you had to choose. Either the principle of relativity was correct, or the speed of light was constant, but not both. They seemed contradictory. Einstein said no, both are true. And if both are true, then our understanding of space and time has to change. The logic is actually straightforward, once you accept the postulates. Imagine you and I are moving relative to each other. I shine a light beam. We both measure its speed. According to the second postulate, we both get the same answer, the speed of light. But we're moving relative to each other. So in Newton's framework with absolute space and absolute time, we should get different answers. We don't. So absolute space and absolute time can't be correct. What has to give? Einstein realized that simultaneity has to give. Time has to give. Space has to give. The very concepts we thought were absolute and fixed have to be flexible and relative. If the speed of light is constant, then time must pass at different rates for observers in relative motion. It has to. There's no other way to make the math work. If you and I are moving relative to each other and we both measure light traveling at the same speed, then our clocks must be ticking at different rates. Time itself must be relative. And if time is relative, then space must be relative too. If we disagree about when things happen, we must also disagree about where things happen. Length must change with motion, just like time does. Einstein didn't just propose this as a vague philosophical idea. He worked out the exact mathematics. He derived the equations, now called the Lorentz transformations, that tell you precisely how time and space change when you move from one reference frame to another. He showed exactly how time dilation and length contraction depend on velocity. The paper was dense, mathematical, and utterly radical in its implications. Einstein was saying that there is no absolute time. There is no universal now. There is no absolute space. Everything we thought was fixed and certain about the structure of reality was actually relative, depending on your motion. And here's the thing. Einstein's proposal made testable predictions. If time really does slow down for moving objects, we should be able to measure that. If lengths really do contract, we should be able to detect that. His theory wasn't just philosophy. It was physics, making specific, quantitative predictions about how the universe works. But the predictions were so strange, so contrary to everyday experience, that many physicists were skeptical. Some thought Einstein must have made a mistake. Others thought maybe the mathematics worked but didn't reflect physical reality. The idea that time itself could be relative seemed too bizarre to be true. Yet, as experiments got more precise, Einstein's predictions kept being confirmed. Again and again and again. Time dilation was real. Length contraction was real. The relativity of simultaneity was real. Reality actually worked the way Einstein said it did, not the way Newton said it did. What Einstein had done was more than just solve the puzzle of the constant speed of light. He had revealed that space and time, these things we thought we understood, these things that seemed so separate and absolute, were actually interconnected and relative. He had shattered our entire framework for understanding reality and replaced it with something new. This was special relativity. And it was just the beginning. Let's talk about what might be the single most mind-bending consequence of Einstein's theory: time dilation. The idea that time itself can slow down or speed up depending on how fast you're moving. This isn't an illusion. This isn't a trick of measurement. This is time itself, the actual ticking of clocks, the actual aging of objects, the actual duration of processes, genuinely passing at different rates for different observers. Here's the scenario Einstein used to derive it. Imagine a light clock. It's just two mirrors facing each other with a pulse of light bouncing between them. Each time the light makes a round trip. That's one tick of the clock. Now imagine this clock is on a spaceship moving past you at high speed. From your perspective, watching the spaceship go by, that light pulse isn't just bouncing straight up and down. It's also moving sideways along with the spaceship. So the light has to travel a longer diagonal path to get from the bottom mirror to the top mirror and back down again. It's traveling a longer distance. But remember the key principle. The speed of light is constant. The light is traveling a longer path, but at the same speed. Longer distance at the same speed means more time. So from your perspective, each tick of that moving light clock takes longer than a tick of an identical clock sitting stationary next to you. The moving clock is running slow. Time is passing more slowly on the moving spaceship. And here's the crucial part. This isn't just about light clocks. This is about time itself. If the light clock on the spaceship is running slow, then every clock on the spaceship is running slow. Mechanical clocks, atomic clocks, biological processes, radioactive decay, the beating of hearts, the firing of neurons, everything. Time itself is dilated, stretched out for the moving observer. The faster you move, the more extreme this effect becomes. At everyday speeds, it's utterly negligible. If you drive across the country at highway speeds, you'll age perhaps a few nanoseconds less than someone who stayed home. Completely unmeasurable without atomic clocks. But at a significant fraction of the speed of light, the effect becomes dramatic. Move at 90% of the speed of light, and time slows down to about 44% of its normal rate. A clock moving at that speed ticks less than half as fast as a stationary clock. Travel for what you experience as 1 year at that speed, and more than 2 years will have passed back on Earth. Get close to the speed of light, and the effect becomes enormous. At 99.9% of the speed of light, time slows to about 4.5% of normal. Travel for 1 year, and 22 years pass on Earth. At 99.99%, 1 year for you is over 70 years for everyone else. This leads to what's called the twin paradox, though it's not really a paradox once you understand the physics. One twin gets on a spaceship and travels to a distant star at near light speed, then returns. The other twin stays on Earth. When the traveling twin returns, they've aged perhaps 5 years. Their twin who stayed home has aged 50 years. They're actually physically younger. Their cells have divided fewer times. Their heart has beaten fewer times. They've experienced less time. This has been tested, not with humans traveling to distant stars. We don't have that technology, but with precise atomic clocks. Put an atomic clock on an airplane, fly it around the world, and when it lands, it's slightly behind a clock that stayed on the ground, exactly as much as Einstein's equations predict. We see it in particle accelerators. Unstable particles that normally decay in microseconds last much longer when accelerated to near light speed. From their reference frame, they're only experiencing microseconds. From our reference frame watching them, much more time is passing. They decay exactly when they should according to their own internal clock. It's just that their clock is running slow compared to ours. GPS satellites have to account for time dilation. They're moving fast relative to us on the ground, so time runs slightly slower for them. If we didn't correct for this, GPS coordinates would drift by kilometers every day. The fact that your phone can tell you your location to within a few meters is proof that time dilation is real. But here's what really bends the mind. From the perspective of the moving observer, their time is normal. They don't feel time running slowly. Their clocks seem fine. Their heartbeat seems normal. It's your time that's running slowly, because you're the one moving relative to them. This is the relativity part of relativity. There's no absolute answer to whose time is running slowly. It depends on your frame of reference. Both observers are correct from their own perspective. Time really is relative. This shattered the Newtonian idea of absolute, universal time. There is no cosmic clock ticking the same for everyone, everywhere. Time is local. Time is personal. Time is relative to your motion. The universe doesn't have a single objective timeline. It has as many timelines as there are observers, all of them equally valid, all of them different. And if you think time dilation is weird, wait until you hear about what happens to space. Time isn't the only thing that changes with motion. Space does too. Objects moving at high speeds actually become physically shorter in the direction of their motion. This is called length contraction, and it's just as real as time dilation. Imagine a spaceship that's 100 meters long, sitting stationary in space. You measure it with a ruler, 100 meters, nose to tail. Now imagine that spaceship accelerates to 90% of the speed of light and flies past you. You measure it again as it passes. It's not 100 meters anymore. It's about 44 meters long. The spaceship has physically contracted. Not just the physical structure of the spaceship, everything inside it contracts too. The distance between the front and back, the space between atoms in the hull, the distance from one side of a cabin to the other, all of it compressed in the direction of motion. And here's the thing that makes this extra strange. From the perspective of the people on the spaceship, nothing has changed. They measure their spaceship, and it's still 100 meters long. The chairs are the same distance apart. The hallway is the same length. Everything is normal. But when they look out the window at you, you appear contracted. From their perspective, you're the one moving, so you're the one who's shortened. The space station you're on is compressed. The planet behind you is flattened like a pancake. Both perspectives are correct. There's no absolute answer to the real length of the spaceship. Length is relative, just like time. The mathematics of this comes straight out of the same framework as time dilation. In fact, they're intimately connected. To understand why, think about that spaceship passing you at 90% of light speed. From your perspective, time is running slowly on the ship. The crew is moving in slow motion. But they don't think they're moving in slow motion. From their perspective, time is normal. So how do they not notice? The answer is that the distances they're traveling are contracted. Say they're traveling to a star that's 10 light years away from your perspective. At 90% light speed, you'd calculate it takes them about 11 years to get there. But their clocks only tick for about 5 years because of time dilation. From their perspective, are they somehow moving faster than 90% light speed? No. From their perspective, the distance to the star is only about 4.4 light years because of length contraction. They travel 4.4 light years in 5 years at 90% light speed. The math works out time dilation and length contraction are two sides of the same coin. They have to exist together to make the constant speed of light work out consistently from all reference frames. And like time dilation, this has been tested. We can't accelerate spaceships to relativistic speeds, but we can accelerate particles. When we do, they behave exactly as if length contraction is real. Particle colliders have to account for it in their designs. The particles are moving so fast that the entire circumference of the accelerator ring is contracted from their perspective. We see indirect evidence of length contraction in cosmic rays. High-energy particles from space slam into the upper atmosphere and create showers of other particles. Some of these particles are muons, which decay very quickly. They have a half-life of only about 2 microseconds. Even moving at near light speed, they should only travel about 600 meters before decaying. But we detect muons at sea level. The upper atmosphere is tens of kilometers high. How do they make it all the way down? From our perspective, it's because time dilation means they decay more slowly. Their internal clocks are running slow, so they last longer. From the muons' perspective, they're not lasting longer. Their proper time is normal. Instead, the atmosphere is contracted. From their reference frame, the distance from the upper atmosphere to the ground is only a few hundred meters, which they can cross before decaying. Both explanations are correct. Both are different ways of describing the same physical reality. Now you might wonder, what happens if you could accelerate to the speed of light? Would you be infinitely time dilated and infinitely length contracted? Would the entire universe in your direction of travel be compressed to zero thickness? Would time stop completely? The answer is that this question doesn't make sense because you can't accelerate to the speed of light. As you approach light speed, several things happen. Time dilation becomes extreme. Length contraction becomes extreme. And, this is crucial, your mass effectively increases, making it harder and harder to accelerate further. It would take infinite energy to actually reach light speed. Only massless particles, like photons, can travel at the speed of light. And from a photon's perspective, if we can even talk about such a thing, the universe is infinitely contracted and no time passes at all. A photon, emitted from a distant star and absorbed by your eye, doesn't experience any time between emission and absorption. From its perspective, if it has one, the journey is instantaneous across zero distance. But we're getting ahead of ourselves. The key point is that space contracts with motion, just as time dilates. And this isn't just a mathematical trick. This is reality. Space and time are actually physically different for observers in relative motion. And this leads us to an even stranger realization. If time is relative and space is relative, then even the concept of now is relative. Here's where things get truly bizarre. Not only do moving observers disagree about how fast time passes and how long objects are, they also disagree about whether events are simultaneous. Events that happen at the same time for one observer happen at different times for another observer moving relative to them. Let me say that again because it's important. There is no universal now. There is no cosmic present moment that spans the entire universe. When you say right now, what you mean depends on how you're moving. Einstein explained this with a thought experiment involving a train. Imagine a train moving at high speed and someone standing in the exact middle of the train. Lightning strikes both ends of the train, the front and the back, at exactly the same time, according to someone standing on the ground watching the train pass. The light from both strikes reaches the ground observer at the same time, so they conclude the strikes were simultaneously. But what about the person on the train? They're moving toward the front of the train, so they're moving toward the light coming from the front strike and moving away from the light coming from the back strike. The speed of light is constant for all observers, so both light beams approach them at the same speed, but they're moving toward one and away from the other. Result: the light from the front strike reaches them first. They see the front strike happen, then a moment later they see the back strike happen. From their perspective, the front was struck first, then the back was struck later. Who's right? Both are right. The strikes really were simultaneous in the ground frame. The strikes really were not simultaneous in the train frame. Both statements are true. Simultaneity is relative. This isn't just about when you see things happen, it's about when they actually happen. The relativity of simultaneity is a real physical effect, not an optical illusion. The events genuinely occur in different orders for different observers. Think about what this means. Imagine an astronaut on a distant planet does something, let's say they clap their hands. You might say that clap is happening right now, from your perspective on Earth. But someone moving at high speed relative to you would disagree. For them, the clap might be in the past. For someone else moving in the opposite direction, it might be in the future. Events that are now for you are in someone else's past or future, depending on how they're moving. There's a whole range of events throughout the universe that different observers will categorize as past, present, or future, and they're all correct from their own frames of reference. Now, before you start worrying about paradoxes, there's an important limitation. You can't use this to send messages backward in time, or anything like that. Events can only appear in different orders if they're far enough apart in space and close enough together in time that light couldn't travel between them. Events that are causally connected, where one could influence the other, maintain their order for all observers. This is encoded in what's called the light cone structure of spacetime, which we'll get to later. But the basic principle is, if event A could cause event B, all observers agree that A happened before B. But if events A and B are far apart and couldn't possibly influence each other, different observers can disagree about their order. The relativity of simultaneity has another profound implication. If different observers disagree about what's happening now in distant locations, then the present moment is not a well-defined concept across the universe. The past, present, and future don't divide up the universe into three distinct categories. Instead, they're relative concepts that depend on your state of motion. This completely undermines our intuitive understanding of time as something that flows uniformly, carrying the entire universe forward from past to future. There is no universal present moment that sweeps across all of space. There is no cosmic now. And here's perhaps the most philosophically disturbing aspect. If there's no universal now, if different observers disagree about what exists simultaneously, then in what sense do distant events exist? Does the distant planet exist right now? The question doesn't have a single answer. It depends on your motion. Some physicists and philosophers take this to mean that all of space-time, past, present, and future, exists equally, that the universe is a four-dimensional block where all moments exist simultaneously, and our experience of moving through time is just our particular way of slicing through that block. But we're getting into deep philosophical territory now. The point is that simultaneity, like time and length, is not absolute. It's relative. It depends on your reference frame. And this means that space and time are not separate, independent things that can be treated separately. They're fundamentally intertwined. They're parts of a single, unified structure, a structure that Hermann Minkowski would name spacetime. In 1908, 3 years after Einstein published his special relativity paper, Hermann Minkowski gave a lecture that would fundamentally change how we think about the structure of reality. Minkowski had been one of Einstein's mathematics professors, and he took Einstein's physics, and revealed the deeper geometric structure underlying it. Minkowski's opening statement was dramatic. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What did he mean by this? He meant that space and time are not separate things. They're not independent entities that happen to be related. They're different aspects of a single, unified, four-dimensional structure: space-time. Think about how we normally think of the world. 3 dimensions of space: length, width, height, and then separately, 1 dimension of time. We can move freely through space, but time just ticks forward. They seem fundamentally different. But Minkowski realized that special relativity reveals something profound. Space and time get mixed together when you change reference frames. A time interval in one frame becomes partly a space interval in another frame. A space interval in one frame becomes partly a time interval in another frame. They're not separate. They transform into each other. It's like the way that east and north get mixed together when you rotate your map. East and north are not independent things. They're directions in a 2-dimensional space. When you rotate your perspective, what was east becomes partly north, and what was north becomes partly east. But the actual distance between 2 points doesn't change when you rotate your map. There's an invariant quantity, the distance, that's the same regardless of how you orient your coordinate system. Minkowski showed that space-time has something similar: the space-time interval. While different observers disagree about the spatial distance between events and disagree about the time between events, they all agree on the space-time interval. The formula for the space-time interval looks like this: space-time interval quadrates equals time interval quadrates. The negative sign is crucial. It's what makes space-time different from ordinary 4-dimensional space. It means time and space have opposite roles in the geometry. This interval is what's actually invariant, what's actually the same for all observers. You and I might disagree about how much space and how much time separates 2 events, but we'll calculate the same space-time interval between them. Let me give you an example. Imagine 2 events. A light is turned on, then turned off 1 second later, in the same location. For an observer at rest relative to the light, the spatial distance between these events is 0, and the time is 1 second. For an observer moving past the light, the 2 events happen at different locations. The light moves between when it's turned on and off. So, there's a spatial distance. And because of time dilation, the time between the events is different too. But both observers calculate the same space-time interval. The moving observer's increased spatial distance and changed time interval combine in exactly the right way to give the same result. This revealed that space-time has a geometry, just like space does. But it's not the familiar geometry of Euclid that we learn in school. It's a different kind of geometry called Lorentzian or pseudo-Riemannian geometry, where time and space have opposite signs in the metric. In this geometry, a straight line through space-time is the path of an object moving at constant velocity. We call these paths world lines. Every object traces out a world line through space-time, and the length of that world line, measured using the space-time interval, is the proper time experienced by that object. This is why time dilation happens. 2 observers who follow different world lines through space-time between the same 2 events will accumulate different amounts of proper time along their paths. They literally experience different amounts of time, not because time is an illusion, but because they're taking different paths through the geometry of space-time. Minkowski's insight was that special relativity isn't really about time slowing down and space contracting. It's about the geometry of space-time. All those weird effects, time dilation, length contraction, relativity of simultaneity, they're all just consequences of the fact that we live in a 4-dimensional space-time with a particular geometric structure. This was a revolutionary shift in perspective. Einstein had shown that space and time are relative. Minkowski showed that space-time is absolute. There's a real, objective, geometric structure to the universe, It's just four-dimensional and has a weird metric where time and space have opposite signs. And here's the beautiful part. Once you understand space-time geometry, special relativity becomes simple. All those confusing formulas and seeming paradoxes resolve into straightforward geometry. You're just calculating distances and angles in a four-dimensional space with an unusual metric. Einstein himself initially dismissed Minkowski's approach as unnecessarily mathematical, but later he would realize that Minkowski's geometric formulation was exactly what he needed to extend relativity to include gravity. The geometric view of space-time would become the foundation for general relativity. But even in special relativity, even without gravity, Minkowski's space-time is the right way to think about it. Space and time really are unified. They really are parts of a single structure. We experience them separately because we're moving through space-time in a particular direction. Our world line points mostly in the time direction, with a little bit in the space directions. But fundamentally, it's all space-time. Four-dimensional, geometric, absolute space-time. And once you can visualize this structure, once you can think in terms of world lines and light cones and space-time diagrams, relativity stops being confusing and starts being beautiful. If space-time is a four-dimensional geometric structure, how do we visualize it? We can't really picture four dimensions, three of space plus one of time. Our brains evolved to handle three spatial dimensions, and four is just beyond our direct intuitive grasp. Minkowski solved this by creating diagrams that show one dimension of space and one of time, suppressing the other two spatial dimensions. These diagrams, called Minkowski diagrams or spacetime diagrams, are one of the most powerful tools we have for understanding relativity. Here's how they work. Draw a graph. The vertical axis is time, pointing upward into the future. The horizontal axis is space, extending left and right. Each point on this diagram represents an event, something happening at a particular location at a particular time. Now, plot the history of an object on this diagram. If an object is sitting still, its position in space doesn't change while time advances, so it traces out a vertical line. This line is the object's world line, its entire history through space-time represented as a single geometric object. If an object is moving at constant velocity, its world line is a straight line tilted at an angle. The faster it moves, the more tilted the line. An object moving to the right has a world line tilted to the right. An object moving to the left has a world line tilted to the left. But there's a limit to how tilted a world line can be. Remember, nothing can move faster than light, so world lines can't be tilted more than 45 degrees from the vertical. A light beam moving to the right traces out a line at exactly 45 degrees to the right. A light beam moving to the left traces out a line at exactly 45 degrees to the left. These two 45-degree lines form a boundary, a cone shape in the full four-dimensional space-time. This is called the light cone. Every event has a light cone, and it divides space-time into three regions. The future light cone contains all events that this event could potentially influence. If you send a signal from here, it can reach anywhere inside your future light cone. The past light cone contains all events that could potentially have influenced this event. Signals from anywhere in your past light cone could have reached you. And the region outside both light cones contains events that are too far away and too close in time to have any causal connection with this event. This structure is fundamental to causality and relativity. Cause and effect can only operate within the light cones. Events outside your light cone are, in a real sense, disconnected from you. They can't affect you, and you can't affect them. Now here's where Minkowski diagrams become really powerful. When you change reference frames, when you look at space-time from the perspective of a moving observer, the diagram changes. The axes tilt. The moving observer's world line becomes vertical in their own frame, and everything else tilts relative to them. Remarkably, the light cones don't change. The 45-degree light beams stay at 45 degrees no matter how you tilt the coordinate system. This is another way of seeing that the speed of light is constant for all observers. The light cone structure is invariant. But the lines of simultaneity, the horizontal lines representing now for a particular observer, those do change. When you change frames, the lines of simultaneity tilt. Events that are simultaneous for one observer are not simultaneous for another observer. You can literally see the relativity of simultaneity in the tilting of these lines. You can also see time dilation and length contraction in these diagrams. A moving clock's ticks are farther apart along its tilted world line. A moving object's length is the distance between its world line endpoints at a particular time. But particular time means different things for different observers because simultaneity is relative. Everything about special relativity, all the weird effects, all the seeming paradoxes, can be visualized and understood using Minkowski diagrams. They translate the mathematics into geometry, making the abstract concrete. Let's take the twin paradox as an example. Draw the Earth's world line as a vertical line. Draw the traveling twins' world line, starting from Earth, tilting away to the right as they accelerate toward a distant star, then tilting back to the left as they turn around and return to Earth. The two world lines start at the same event and end at the same event, but they take different paths through spacetime. The length of each world line, measured using the spacetime interval, is the proper time experienced along that path. The traveling twins' world line is longer in space, but shorter in spacetime. They experience less proper time. You can literally see that they age less by comparing the lengths of the world lines in the spacetime metric, or consider the relativity of simultaneity. Draw two observers moving past each other. Their lines of simultaneity are tilted relative to each other. An event that's in the future for one observer is in the past for the other. You can see it right there in the diagram. Minkowski diagrams aren't just teaching tools. They're used by physicists to solve real problems in relativity. When you want to analyze a complex scenario involving multiple observers moving at different velocities, you draw a spacetime diagram. The geometry tells you what's happening. And the beauty of these diagrams is that they make the geometric nature of spacetime obvious. You're not doing abstract mathematics. You're doing geometry. You're measuring intervals, calculating angles, comparing world lines. It's the same kind of reasoning you'd use to solve problems in regular Euclidean geometry, just with a different metric. This geometric view, seeing spacetime as a real concrete structure that we can draw and measure and analyze, was Minkowski's great contribution, and it set the stage for Einstein's next breakthrough. Because if space-time is a geometric structure in special relativity, where everything is moving at constant velocity in the absence of forces, what happens when you include gravity? What happens when objects accelerate? Could gravity itself be a manifestation of space-time geometry? That question would lead to general relativity. But before we get there, we need to understand more about what these diagrams are showing us, what the light cone structure really means, and what it tells us about the fundamental nature of causality and reality itself. Let's go deeper into what those light cones really mean, because they're not just a mathematical abstraction. They represent the fundamental causal structure of the universe. They tell you what can affect what, what's connected to what, what's even meaningful to talk about as connected. Take any event in space-time. Right now, reading these words, that's an event. Call it Event E. From Event E, imagine light beaming out in all directions, forward, backward, left, right, up, down. In a space-time diagram with two spatial dimensions and one time dimension, these light beams trace out a cone shape pointing into the future. That's your future light cone. Everything inside that future cone is accessible to you. If you want to influence something, if you want to send a signal, if you want to cause something to happen, it has to be inside your future light cone. Anything outside that cone is unreachable, Not just practically unreachable, fundamentally, absolutely unreachable. You cannot affect it. You cannot send it information. You cannot interact with it in any way whatsoever. Now imagine light beams converging on event E from all directions in the past. These trace out another cone, pointing backward in time. That's your past light cone. Everything inside that past cone could potentially have influenced event E. Every cause, every signal, every piece of information that affects you right now must have originated somewhere in your past light cone. And then there's the region outside both cones, events that are too far away in space and too close to you in time. These events are space-like, separated from you. They're elsewhere. They're in a completely different category from past and future. Here's what's strange about the elsewhere region. Events in this region have an ambiguous relationship with you. Some observers will say these events are in your past. Other observers will say they're in your future. Both are correct. The ordering is relative, because simultaneity is relative. But it doesn't matter, because these events can't causally interact with you anyway. They're outside your light cone. This is why relativity doesn't lead to time travel paradoxes. Yes, different observers disagree about the order of events in the elsewhere region, but causally connected events, events where one could actually influence the other, maintain their order for all observers. The light cone structure ensures this. If event A is in event B's past light cone, then all observers agree that A happened before B. Causality is preserved. The light cone structure also gives us a rigorous definition of what we mean by now in relativity. Your present moment, the set of all events happening now, is a slice through spacetime. But which slice? Different slices correspond to different states of motion. There's no unique present moment, but there is something unique, the boundary between your past and future light cones. This is your light sphere, the set of all events that light could be reaching you from right now, or that you could be sending light to right now. This is observer independent. All observers agree on what's on your light cone, even if they disagree about what's in your past versus future versus elsewhere. The light cone structure also tells us something profound about the speed of light. Why is the speed of light the cosmic speed limit? Why can't anything go faster? Because the light cone defines what faster and slower even mean in spacetime. Going faster than light doesn't just mean going really fast. It means leaving your light cone, crossing into the elsewhere region, entering the domain of events that should be space-like, separated from you. It means breaking the causal structure of the universe. If you could travel faster than light, you could affect events in your elsewhere region. And since the ordering of events in the elsewhere region is relative, this would allow different observers to disagree about cause and effect. You could have situations where one observer sees A cause B, and another observer sees B cause A. You'd have causal loops, grandfather paradoxes, effects preceding causes. The entire logical structure of causality would break down. The speed of light isn't just a speed limit, it's the boundary of causality itself. It's what separates events that can affect each other from events that can't. It's the structure that makes the universe make sense. And here's something even more mind-bending. As you move through space-time, your light cones tilt. The set of events in your past light cone is constantly growing as you move into the future. More and more events enter your past light cone as time advances. Your past is growing, but the events in your elsewhere region, the events that are space-like, separated from you right now, those change too. Some of them are entering your past light cone. Some of them are entering your future light cone. The elsewhere region is shrinking as you move forward through time, with events constantly moving from elsewhere into your past or future. This means there are events happening right now in distant galaxies that are in your elsewhere region. You can't know about them yet. They haven't entered your past light cone. The light from them hasn't reached you. But in the future, They will enter your past light cone. You will be able to receive information about them. They'll transition from elsewhere to past, and there are other events in those distant galaxies that will never enter your past light cone. If the universe is expanding, and if that expansion is accelerating, then there are galaxies so far away that light leaving them now will never reach us. They're in our elsewhere region now, and they'll remain in our elsewhere region forever. We are fundamentally, absolutely disconnected from those events. The light cone structure divides space-time into domains of possible influence, domains of possible knowledge, and domains of permanent disconnection. It creates a network of what can affect what can know about what can interact with what. This is the causal structure of the universe. In Newtonian physics, this structure didn't exist. Information could travel infinitely fast. Everything could affect everything else instantaneously. The entire universe had a well-defined present moment, and everything in that present moment could potentially interact. There was no fundamental limit to the spread of causality. But in relativity, the light cone structure is fundamental. It's built into the geometry of space-time itself. It's not a limitation imposed by technology or by the properties of matter. It's a limitation imposed by the structure of reality. Causality itself has a speed limit, and that speed limit is the speed of light. This structure, this light cone architecture, this causal geometry, it's one of the deepest features of our universe. It tells us how reality is organized at the most fundamental level. It tells us what's possible and what's not, what's connected and what's isolated, what's real and what's ambiguous. And all of this, time dilation, length contraction, relativity of simultaneity, the light cone structure, all of this comes from special relativity. From just taking seriously the constant speed of light and following the implications to their logical conclusion. But special relativity only works for inertial reference frames, observers moving at constant velocity, not accelerating. What happens when you include acceleration? What happens when you include gravity? That's where things get really interesting. Because Einstein was about to realize that gravity itself is fundamentally connected to the geometry of space-time. Not just in some metaphorical sense. Literally, physically, gravity is the curvature of space-time. And the key to this realization came from one of the simplest thought experiments imaginable. A person falling in an elevator. Picture this. You're in an elevator. The cable snaps. You start falling. What do you feel? Nothing. You feel weightless. You and the elevator are both falling at the same rate. So from your perspective inside the elevator, you're just floating there. If you let go of your phone, it floats next to you instead of falling to the floor. The floor isn't rushing up to meet you because it's falling at exactly the same rate you are. Now imagine a different scenario. You're in that same elevator, but it's in deep space, far from any planet or star. No gravity, just you and the elevator floating in empty space. You feel exactly the same thing. Weightlessness. You can't tell the difference between freely falling in a gravitational field and floating in space with no gravity at all. This is the equivalence principle, and it was Einstein's key insight that led him from special relativity to general relativity. But let's flip it around. Imagine you're in an elevator in deep space again, but now someone's pulling the elevator upward with a rocket, accelerating it at exactly 9.8 meters per second squared, the same acceleration as Earth's gravity. You'd feel a force pushing you into the floor. If you let go of your phone, it would fall to the floor, not because gravity is pulling it down, but because the floor is accelerating up to meet it. Now imagine you're in an elevator on Earth, sitting still. You feel a force pushing you into the floor. If you let go of your phone, it falls. Einstein's realization, you cannot tell the difference between these two situations. Being in an accelerating elevator in empty space feels exactly the same as being in a stationary elevator in a gravitational field. There is no experiment you can do inside the elevator to distinguish between acceleration and gravity. This seems simple. maybe even obvious, but it's profound. Because in Newtonian physics, gravity and acceleration are fundamentally different things. Gravity is a force that masses exert on each other. Acceleration is just change in velocity. They're not the same kind of thing at all. But Einstein realized they're indistinguishable from each other. They produce exactly the same effects. They're equivalent. Now, let's think about what this means for light. In special relativity, we know that light travels in straight lines through empty space-time. But what if space-time isn't empty? What if there's a gravitational field? Einstein reasoned like this. Imagine you're in that accelerating elevator in deep space. You shine a laser horizontally across the elevator. From your perspective inside the elevator, the laser beam curves downward. Why? Because by the time the light crosses the elevator has accelerated upwards, so from your reference frame, the light has curved down. But the equivalence principle says that acceleration and gravity are indistinguishable. So if light curves in an accelerating elevator, it must also curve in a gravitational field. Gravity must bend light. This was shocking. In Newton's theory, light has no mass, and gravity only affects things with mass, so gravity shouldn't affect light at all. But Einstein was saying that gravity absolutely must affect light. It has to, because of the equivalence principle. And if gravity bends light, and light in special relativity travels along the straightest possible paths through space-time, then maybe gravity isn't bending light at all. Maybe gravity is curving space-time itself, and light is still traveling in straight lines, but those straight lines are through curved space-time. Think about it this way. Imagine drawing a straight line on a flat piece of paper. The line is straight. Now wrap that paper around a sphere. From the perspective of someone on the sphere's surface, that line now appears curved. But the line hasn't actually bent. It's still the straightest possible path. The space itself has curved. Einstein realized that gravity works the same way. Objects in free fall, objects not being pushed or pulled by anything other than gravity, are actually moving along the straightest possible paths through space-time. It's just that space-time itself is curved by the presence of mass and energy, so those straight paths look curved to us. When you drop a ball and it falls to the ground, the ball isn't being pulled by a force. It's following the curvature of space-time, caused by Earth's mass. The ball is moving in a straight line through curved space-time, and that straight line happens to point toward the center of the Earth. And when you're standing on the ground, you're not in free fall. The ground is pushing up on you, accelerating you away from your natural straight-line path through space-time. That's why you feel weight. You feel the ground pushing on you, preventing you from following your natural geodesic path. This is the deep insight of the equivalence principle. Free fall is the natural state. When you're falling, you're not accelerating, you're moving inertially through curved space-time. When you're standing on the ground, you are accelerating. The ground is pushing you away from your inertial path. Einstein spent years trying to turn this insight into a mathematical theory. The equivalence principle told him that gravity must be geometry, that space-time must be curved, that free-falling objects follow geodesics through that curved space-time. But how exactly does mass curve space-time? What are the equations? The equivalence principle only works locally. In a small enough region of space-time, you can't tell the difference between gravity and acceleration. But globally, gravity and acceleration are different. In a gravitational field, objects at different locations fall in different directions toward the center of the gravitating mass. In a uniformly accelerating reference frame, everything accelerates in the same direction. So Einstein needed equations that would describe not just local curvature, but the global geometric structure of space-time. He needed to learn differential geometry, Riemannian geometry, tensor calculus, mathematical tools that didn't normally come up in physics. He struggled with this for years. It was mathematically incredibly difficult. But in 1915, he finally got it. He found the equations that describe how matter and energy curve space-time, and how that curvature determines the motion of matter and energy. Those equations would be called the Einstein field equations, and they would reveal that our universe is far stranger than anyone had imagined. Let's be clear about what Einstein was proposing, because it's radical. He wasn't just saying that gravity affects space-time, or that we can use geometric language to describe gravity. He was saying that gravity is geometry, literally, physically. Gravity is not a force at all. It's the curvature of space-time itself. In Newton's theory, gravity is a force. Mass attracts mass. The Earth pulls on you, you pull on the Earth. The Sun pulls on the Earth pulls on the Sun. These are forces transmitted somehow across empty space, causing objects to accelerate. Einstein said, no, there are no gravitational forces. Mass and energy curve the fabric of space-time, and objects simply follow the straightest possible paths, geodesics, through that curved space-time. What we perceive as gravitational attraction is just the geometry of space-time telling objects how to move. John Wheeler, one of the great relativists of the 20th century, summarized it perfectly. Space-time tells matter how to move, matter tells space-time how to curve. But what does it mean for space-time to be curved? We can visualize a curved surface, like a sphere or a saddle, but space-time is four-dimensional. 3 of space, 1 of time, and it has that weird Lorentzian signature where time and space have opposite signs. How do we even think about curvature in such a space? Here's one way to think about it. In flat space-time, the space-time of special relativity with no gravity, parallel lines stay parallel. If two objects start moving in parallel paths, they continue moving in parallel paths forever. But in curved space-time, parallel paths can converge or diverge. Imagine two people standing on the equator of the Earth, a few meters apart, both starting to walk straight north. At first, they're walking parallel to each other. But as they walk toward the North Pole, they get closer and closer together. Eventually, they meet at the pole. Their paths converged, even though they were both walking in straight lines. Why? Because the Earth's surface is curved. Space-time curvature works similarly. Two objects in free fall, initially moving in parallel, can have their paths converge or diverge because the space-time through which they're moving is curved. If they're both falling toward a massive object like Earth, their paths converge. They get closer together over time. We interpret this as gravitational attraction, but really it's just geometry. The curved space-time makes their geodesic paths point toward each other. This also explains tidal forces. Imagine you're falling toward Earth feet first. Your feet are slightly closer to Earth's center than your head is. The geodesic through space-time at your feet points at a slightly different angle than the geodesic at your head. Both point toward Earth's center, but from different starting points. So the path your feet want to follow and the path your head wants to follow actually diverge slightly. You get stretched. These are tidal forces, and they're just the manifestation of space-time curvature varying from place to place. Now, time is also curved by gravity, not just space. In fact, for most gravitational situations we encounter, the curvature of time is more significant than the curvature of space. When you drop a ball, it's primarily the curvature of time, the temporal component of the space-time metric, that causes it to fall. The ball is moving primarily through time, and the curvature of time tells it to also start moving through space, toward the source of gravity. Think about what this means. You're sitting in your chair right now, and you think you're not moving, but you are moving through time. You're constantly moving into the future, at 1 second per second. And because space-time near Earth is curved, that motion through time gets converted into motion through space. If the chair weren't holding you up, you'd start moving downward. You're constantly falling through time, and the curvature converts that into spatial motion. The stronger the gravitational field, the more curved space-time is. Near Earth's surface, the curvature is relatively gentle. You fall at 9.8 meters per second squared, but near a neutron star, the curvature is extreme. Fall toward that, and you'd be torn apart by tidal forces long before you hit the surface. The difference in curvature between your head and feet would be enormous, and at the center of a black hole, the curvature becomes infinite. The equations break down. We'll get to that nightmare later. But here's what's beautiful about this geometric view. It explains why everything falls at the same rate. In Newtonian gravity, it's a mysterious coincidence that gravitational mass equals inertial mass. Why should the property that determines how much gravity pulls on you be exactly equal to the property that determines how much you resist acceleration? Newton couldn't explain this. He just observed that it was true. But in Einstein's theory, there's no mystery. Everything falls at the same rate because they're all following the same geometry. A feather and a hammer dropped on the moon fall at the same rate because they're both following geodesics through the same curved space-time. Mass doesn't matter because they're not being pulled by a force proportional to their mass. They're just following the natural paths through space-time. This is what the equivalence principle really means. It's not just that gravity and acceleration feel the same, it's that gravity is geometry, and freefall is inertial motion through that geometry. Now, I've been talking about curvature as if it's a simple concept, but actually, there are different ways space-time can be curved. In mathematical terms, curvature is described by a tensor, the Riemann curvature tensor, which has 20 independent components in 4 dimensions. Different patterns of curvature produce different gravitational effects. There's intrinsic curvature versus extrinsic curvature. Intrinsic curvature is curvature you can measure from within the space itself, without reference to any higher dimension. A sphere has intrinsic curvature. Someone living on the surface could tell it's curved by drawing triangles and measuring their angles. Extrinsic curvature is how a surface bends in a higher dimensional space. A cylinder has extrinsic curvature, but 0 intrinsic curvature. Someone living on a cylinder surface could think it's flat. Space-time has intrinsic curvature. It doesn't need to be embedded in some higher dimensional space. The curvature is a property of the 4-dimensional space-time itself, measurable from within. And that curvature encodes everything about gravity. The trajectory of a planet around the sun, the bending of starlight, the precession of orbits, the gravitational redshift of light, the existence of black holes, the expansion of the universe, all of it comes down to the curvature of space-time. But Einstein still needed the equations. He needed the mathematical relationship between matter-energy and curvature. He needed to know precisely how the distribution of mass and energy determines the geometry of space-time. And in 1915, after years of struggle, he found them. The Einstein field equations are both elegant and terrifying. Elegant because they compress an enormous amount of physics into a compact mathematical form. Terrifying because actually solving them for any realistic situation is brutally difficult. The equations are usually written like this: G mu mu equals 8 pi g sensitivity T mu. On the left side, G mu is the Einstein tensor, which encodes the curvature of spacetime. On the right side, T mu is the stress energy tensor, which encodes the distribution of matter and energy. The equation says the curvature of spacetime, left side, equals the distribution of matter and energy, right side, times some constants. Simple, right? Space-time curvature equals matter-energy distribution. That's Wheeler's summary. Matter tells space-time how to curve. But hidden in this deceptively simple notation is an enormous amount of complexity. The indices mu and nu each run from 0 to 3, representing the 4 dimensions of space-time. So this isn't one equation, it's 16 equations, one for each combination of mu and nu. Actually, because the tensors are symmetric, it's only 10 independent equations, but still 10 coupled, nonlinear, partial differential equations in 4 variables. These are not easy to solve. The Einstein tensor G mu itself is built from the Riemann curvature tensor, which describes how much spacetime deviates from being flat. The Riemann tensor has 80 components in 4 dimensions, though symmetries reduce this to 20 independent components. The Einstein tensor is a particular contraction of the Riemann tensor, a specific way of summing up certain components. The stress-energy tensor T manual describes matter and energy. The component T_00 is energy density, T_0I and T_I0, where I is 1, 2, or 3, describe energy flux and momentum density. T_ij describes momentum flux, which includes pressure and shear stress. Everything that contributes to the gravitational field goes into this tensor: mass, energy, pressure, momentum, stress. The constants on the right side include G, Newton's gravitational constant, and c, the speed of light. These ensure the equation reduces to Newtonian gravity in the appropriate limit, weak fields, and slow speeds. Now here's the mind-bending part. These equations are nonlinear. The curvature of spacetime depends on the distribution of matter and energy, but matter and energy move along geodesics in curved spacetime. So the matter distribution depends on the curvature, which depends on the matter distribution, which depends on the curvature. You have to solve for everything simultaneously. The geometry and the matter distribution have to be mutually consistent. You can't solve for the geometry first and then figure out how matter moves. You have to find a solution where the geometry tells matter how to move, and that motion produces that exact geometry. This is incredibly difficult. For most realistic situations, like a binary star system, or a collapsing star, or the merger of 2 black holes, you cannot solve these equations analytically. You need supercomputers running for weeks to numerically approximate solutions. But for certain highly symmetric situations, we can solve them. A perfectly spherical, non-rotating mass gives the Schwarzschild solution. A rotating mass gives the Kerr solution. A uniform isotropic universe gives the Friedmann-Lemaitre-Robertson-Walker solutions. These exact solutions have taught us an enormous amount about how gravity works. The Schwarzschild solution, for instance, revealed that black holes are possible. Before anyone thought about stellar collapse or event horizons, the mathematics predicted that if you compress enough mass into a small enough region, you get a singularity surrounded by a surface of no return. The math predicted black holes before anyone believed they could exist. The field equations also predicted gravitational waves, ripples in spacetime curvature that propagate at the speed of light. Einstein himself was unsure whether these were real physical waves or just mathematical artifacts. But they're real. We've detected them. The collision of 2 black holes sends gravitational waves rippling through spacetime, and we can measure those ripples here on Earth. Here's another remarkable thing. The equations don't distinguish between mass and energy. E equals mc dibrane from special relativity means mass and energy are equivalent, and the field equations treat them the same way. Energy curves space-time just like mass does. A box full of photons, massless though they are, still curves space-time, because photons carry energy. In fact, pressure and stress also curve space-time. The pressure of the gas inside a star contributes to its gravitational field. Usually this effect is negligible compared to the mass. But in extreme conditions, like the early universe or the interior of a neutron star, pressure matters. The field equations even have a weird property where gravity itself gravitates. The gravitational field carries energy, and energy curves space-time, so the gravitational field generates more gravitational field. This is why the equations are nonlinear and why they're so hard to solve. Gravity generates gravity. The field feeds back on itself. Einstein spent years deriving these equations. He had to learn mathematics that most physicists had never used. He made mistakes. went down wrong paths, second-guessed himself. At one point, he published an incorrect version of the equations. But in November 1915, he finally got them right, and immediately he could test them. Because there was a problem in astronomy that Newton's theory couldn't explain. A tiny anomaly in the orbit of Mercury that had puzzled astronomers for decades. Einstein calculated what his new equations predicted for Mercury's orbit. They matched the observations perfectly. Not approximately, not close enough, perfectly. When Einstein saw this result, he said his heart palpitated. He knew he had found something true about the universe. The equations predicted more than Mercury's orbit, though. They predicted that light bends when it passes near a massive object. They predicted that time runs slower in strong gravitational fields. They predicted the expansion of the universe, though Einstein initially didn't believe this prediction and tried to modify his equations to prevent it. Every prediction that we've been able to test has been confirmed. The equations work. They describe reality. Spacetime really is curved by mass and energy, and that curvature really is what we experience as gravity. But the equations are still deeply mysterious in some ways. We don't have a complete catalogue of all their solutions. We don't fully understand what happens at singularities, where the curvature becomes infinite. We don't know how to reconcile them with quantum mechanics, and we still don't have a deep intuitive understanding of what space-time curvature really is. We can calculate it, measure it, use it to make predictions. But what is it? Is space-time a substance that can be bent? Is it an emergent property of something more fundamental? Is it even real? Or is it just a mathematical description of gravitational phenomena? These questions remain open, but the equations work, and they reveal a universe far stranger than Newton ever imagined. We have a problem. We need to visualize curved spacetime, but spacetime is four-dimensional, and our brains are three-dimensional. We can barely imagine curved three-dimensional space, let alone curved four-dimensional spacetime, with its weird time-space metric. So, we use analogies. The most common one is the rubber sheet analogy. You've probably seen it. Space-time is like a rubber sheet, and massive objects create dimples in the sheet. A planet is like a bowling ball placed on a trampoline, creating a depression. Smaller objects roll around in this depression, appearing to be attracted to the massive object. This analogy gets something right. It gives you a visual sense of what curvature means. The rubber sheet is curved near the massive object, and flatter far away. Objects naturally follow the curved contours, moving toward regions of greater curvature. It's a picture you can hold in your mind, but it gets almost everything else wrong. And understanding what it gets wrong is actually important for understanding what general relativity is really saying. First problem. The rubber sheet analogy requires gravity to explain gravity. Why does the bowling ball create a depression in the sheet? Because Earth's gravity pulls it down. Why do smaller objects roll into the depression? Because Earth's gravity pulls them down the slope. But we're trying to explain gravity. We can't use gravity to explain why curved spacetime produces gravitational effects. That's circular. In real general relativity, there's no external gravitational field pulling things down the curvature. Objects move along geodesics through curved space-time, because that's what objects do. They follow the straightest possible paths through whatever geometry they're in. No external force needed. Second problem. The analogy suggests that gravity is caused by curvature of space, but actually it's mostly the curvature of time that matters. When you drop a ball, it's not rolling down a spatial slope. It's moving through time. And the curvature of time, the fact that time passes at different rates at different distances from a massive object, is what primarily causes the ball to accelerate downward. The ball is moving forward through time, and the gradient in the rate of time's passage converts that motion into motion through space. This is completely invisible in the rubber sheet picture. Third problem. The rubber sheet is two-dimensional, embedded in three-dimensional space. You're looking at the curvature from outside, from the third dimension. But space-time is intrinsically curved. There is no outside, no higher dimension we're embedded in. The curvature is a property of the four-dimensional space-time itself, measurable from within. When we draw a curved surface and look at it from outside, we're showing extrinsic curvature. But space-time has intrinsic curvature. An ant living on the surface of a sphere could determine the sphere is curved without ever leaving the surface, just by measuring the angles of triangles. Similarly, we can measure space-time curvature from within space-time without reference to any higher dimension. Fourth problem. The analogy suggests that massive objects sit in space-time, creating curvature around them. But really, the distribution of mass energy and the geometry of space-time have to be solved for simultaneously. Matter doesn't exist independently and then curve space-time. Matter and space-time curvature are mutually determining. You can't have one without the other. So if the rubber sheet analogy is so flawed, why do we use it? Because despite all its problems, it does capture something essential, that gravity is geometry. Massive objects somehow change the shape of space-time. That shape influences how other objects move. This is fundamentally different from Newton's picture of forces acting across empty space. Are there better analogies? Sort of. Some people use the analogy of ants walking on a curved surface. If the surface curves one way, their paths converge. If it curves another way, their paths diverge. Even if they're both walking straight, the curvature of their space makes their paths bend relative to each other. This gets at the idea of geodesics in curved space, without requiring an external gravitational field. Others talk about rivers flowing on a curved landscape. Water follows the contours of the land, seeking the path of steepest descent. In space-time, objects follow geodesics, seeking the path of extremal proper time. It's not the same thing, but it gives you a sense that motion is determined by geometry rather than forces. Some physicists prefer embedding diagrams, which show how a two-dimensional slice through spacetime is curved. These are mathematically more rigorous than rubber sheets, but they're also more abstract and harder to interpret. The truth is, there's no perfect analogy for curved spacetime. Any lower-dimensional or simpler model leaves out crucial features. The only completely accurate representation is the mathematics, the metric tensor, the curvature tensor, the field equations themselves. But we're not mathematical beings. We're visual beings. We need pictures, even imperfect ones. So we use the rubber sheet, and we use embedding diagrams, and we use ant analogies, and we try to build up an intuition for what curvature means. Here's maybe a better way to think about it. Forget about visualizing the curvature itself. Instead, focus on its effects. Curvature means that initially parallel geodesics converge or diverge. Curvature means that if you go around a closed loop and parallel transport a vector, keep it pointing in the same direction throughout the journey, it ends up pointing in a different direction when you return to where you started. Curvature means the angles of a triangle don't add up to 180 degrees. Curvature means that circumference isn't 2 pi times the radius. These are measurable effects. You don't have to visualize the curvature itself. Just understand what it predicts about measurements. And when those predictions match observations, you know the curvature is real, whether you can visualize it or not. And the predictions do match observations, spectacularly so. Which brings us to the first great test of general relativity, the orbit of Mercury. By the mid-1800s, Newtonian gravity had been tested and confirmed countless times. It explained planetary orbits, predicted the existence of Neptune before anyone saw it, accounted for the tides, described the motion of comets and asteroids. It was one of the most successful scientific theories ever developed. But there was a problem. A tiny problem. A problem with Mercury. According to Newton's laws, planets should orbit the Sun in perfect ellipses, with the Sun at one focus. These ellipses should remain fixed in space. Mercury's orbit should be the same ellipse century after century. Of course, other planets perturb the orbits slightly through their gravitational influence, causing slow changes over time. When you account for all the planet's gravitational effects, you can predict exactly how each orbit should evolve. Astronomers did this calculation for Mercury. They measured Mercury's orbit very precisely over many decades, and they found something strange. Mercury's orbit precesses. The ellipse itself rotates slowly over time. The point of closest approach to the Sun, the perihelion, gradually shifts around. This precession was about 574 arcseconds per century. That's about 0.16 degrees per century, tiny, but measurable with 19th century instruments. Most of this precession could be explained by the gravitational pull of other planets, Venus, Earth, Jupiter. All of them tug on Mercury, causing its orbit to precess. When you add up all these effects using Newtonian gravity, you get about 531 arcseconds per century. But observations showed 574 arcseconds per century. There was a discrepancy of 43 arcseconds per century. That's about 0.012 degrees per century. Utterly tiny, but real. Consistent, unexplained. Astronomers tried everything to explain this. Maybe there was an undiscovered planet even closer to the Sun than Mercury, pulling on it. Some people even named this hypothetical planet Vulcan and claimed to have observed it. But no such planet existed. Maybe the Sun wasn't perfectly spherical. Maybe it had a slight bulge at the equator that created an extra gravitational pull. But the required bulge would be visible, and the Sun doesn't have it. Maybe Newton's law of gravity wasn't exactly an inverse square law. Maybe at very close distances, like Mercury's distance from the Sun, the force falls off slightly faster or slower than one tread. But any modification that fixed Mercury's orbit would break the perfectly good predictions for the other planets. For decades, this was an unsolved mystery, a tiny anomaly in an otherwise perfect theory. Most scientists figured there was some mundane explanation they just hadn't found yet. Few thought it indicated a fundamental problem with Newton's theory. Then Einstein developed general relativity, and one of the first things he did was calculate what his new theory predicted for planetary orbits. In general relativity, planets don't orbit because the Sun exerts a force on them. They orbit because the Sun's mass curves space-time, and the planets follow geodesics through that curved space-time. For a planet orbiting a massive spherical object, the geodesic isn't exactly an ellipse. It's an ellipse that slowly rotates over time. Why? Because space-time curvature is slightly different at different points in the orbit. As the planet moves through regions of different curvature, the geodesic path evolves. The result is a precession of the orbit, exactly what was observed for Mercury. Einstein calculated the predicted precession. The calculation is involved but straightforward. You take the Schwarzschild solution for curved space-time around a spherical mass, calculate the geodesic equations for an object in orbit, and work out how much the orbit precesses per revolution. The answer, 43 arcseconds per century. Exactly what was observed. Not approximately. Not close. Exactly. Within the margin of measurement error, Einstein's prediction matched the unexplained anomaly perfectly. When Einstein realized this, he later said he was so excited that he had heart palpitations. For 3 days, he could barely work. This wasn't just confirming his theory. This was explaining something that Newton's theory, for all its successes, couldn't account for. The beauty of this wasn't just that general relativity got the right number, it's that the theory predicted this precession, with no free parameters, no adjustable constants to fit the data. Einstein didn't tune his equations to match Mercury's orbit. He derived the equations from fundamental principles, the equivalence principle, and the requirement that his theory reduce to newtons in the weak field limit. And the equations automatically, inevitably, predicted Mercury's orbital precession. This was the first empirical victory for general relativity. And it was impressive because it explained an existing anomaly that had puzzled astronomers for decades. Einstein's theory wasn't just making new predictions, it was solving old problems. But there was a catch. This was explaining something that people already knew about. Skeptics could argue that maybe Einstein had unconsciously tuned his theory to match this observation. It would be more convincing if general relativity made a new prediction, something that hadn't been observed yet, that could be tested. And Einstein had exactly such a prediction. Starlight should bend when it passes near the sun, and the amount of bending should be twice as much as you'd predict, even if you tried to account for light being affected by Newtonian gravity. This was testable. You could measure the positions of stars near the sun during a solar eclipse and compare them to their positions when the sun isn't there. If the light bent, the stars would appear to shift position. All anyone needed to do was wait for a solar eclipse and make the measurements. The stage was set for one of the most famous experiments in the history of physics. The year was 1919. World War I had just ended. Europe was in ruins. International scientific collaboration had largely ceased during the war years. British and German scientists had been on opposite sides of a devastating conflict, and yet British scientists were preparing to test a theory developed by a German physicist. The theory was general relativity. The physicist was Albert Einstein, and the test would involve a total solar eclipse. Here's why an eclipse was necessary. Einstein's theory predicted that light from distant stars would bend as it passed near the sun. The sun's mass curves spacetime, and light follows the curvature. A straight line through curved spacetime appears curved from our perspective. This should cause stars near the sun's edge to appear shifted from their true positions. But you can't see stars near the sun under normal circumstances. The sun is too bright. You need the sun's light blocked out. You need a total solar eclipse. Einstein calculated the expected deflection, about 1.75 arcseconds, for starlight grazing the sun's edge. That's about 1/2000th of a degree. Tiny, but measurable, with careful photography and good telescopes. Interestingly, you can calculate a deflection even using Newtonian gravity if you assume light has mass or is affected by gravity. Do this, and you get half of Einstein's prediction, about 0.87 arcseconds. So the eclipse measurement could distinguish between Newtonian gravity, even modified to affect light, and general relativity. The theories made different testable predictions. Arthur Eddington, a British astronomer and one of the few people who understood general relativity at the time, organized expeditions to observe the May 29, 1919, total solar eclipse. He was a Quaker and a pacifist who had opposed the war. Testing Einstein's theory was, for him, a way to demonstrate that science transcends national boundaries, that British scientists could validate a German theory even in the aftermath of a war. 2 teams were sent. One went to Sobral, Brazil. The other, led by Eddington himself, went to the island of Principe off the west coast of Africa. These locations were chosen because the eclipse would pass over them and because the sun would be in front of the Hyades star cluster at the time, providing many bright stars to photograph. The observation was challenging. You photograph the stars near the sun during the eclipse, then months later photograph the same region of sky at night when the sun is elsewhere, and compare the star positions. Any shift in position indicates that light bent when passing near the sun. But there were problems. On Principe, it rained on the morning of the eclipse. Eddington had only a few minutes during totality to capture photographs through breaking clouds. The images weren't as clear as he'd hoped. He managed to get usable measurements from only 2 photographic plates. The Sobral team had better weather but had issues with their main telescope. Temperature changes had defocused it. They did get good images from a backup telescope. After months of careful analysis, measuring star positions on the photographic plates and comparing them to reference photographs, the results came in. The Sobral measurements gave 1.98 plus or minus 0.12 arcseconds. Eddington's Principe measurements gave 1.61 plus or minus 0.30 arcseconds. Both were consistent with Einstein's prediction of 1.75 arcseconds. Both clearly ruled out the Newtonian prediction of 0.87 arcseconds. The announcement was made at a joint meeting of the Royal Society and the Royal Astronomical Society on November 6, 1919. J.J. Thomson, the president of the Royal Society and discoverer of the electron, called it one of the highest achievements of human thought and compared it to the work of Newton. The next day, headlines around the world proclaimed Einstein's theory triumphs. The New York Times ran the headline, "Lights all askew in the heavens." The London Times declared, "Revolution in science and Newtonian ideas overthrown." Overnight, Einstein became world famous, not just famous among physicists, famous to the general public. He became a celebrity, the face of genius, the symbol of scientific revolution. Newspapers wanted interviews. People wanted to understand this strange new theory that somehow curved space and time. There's some irony here. Einstein's work on special relativity in 1905 and his explanation of the photoelectric effect, which helped establish quantum mechanics, were arguably more revolutionary in the long run. But those hadn't captured public imagination. General relativity did, perhaps because it was comprehensible enough to describe in newspaper headlines, "Space is curved," but mysterious enough to seem almost magical. Now, looking back with modern knowledge, those 1919 measurements weren't actually that precise. The error bars were fairly large. The Principi measurements especially were barely good enough to distinguish Einstein's prediction from Newton's. Some historians have questioned whether Eddington's analysis was completely objective. Did he unconsciously favor results that supported Einstein? But subsequent eclipse measurements confirmed the result, and modern measurements using radio astronomy and observations of quasars are far more precise. We now know that light deflection near the Sun matches Einstein's prediction to better than 0.01% accuracy. General relativity was right. The 1919 eclipse expedition wasn't just a scientific milestone, it was a cultural moment. It showed that science could transcend war and nationalism. It demonstrated that our fundamental understanding of reality could change. It made Einstein a household name, and it confirmed that space-time really is curved. Mass really does bend the path of light. Gravity really is geometry. But general relativity predicted more than light deflection. It predicted something even stranger, that gravity affects time itself. Time doesn't just dilate when you move fast, as in special relativity. Time also dilates when you're in a gravitational field. Clocks run slower in stronger gravity. This is gravitational time dilation, and it's just as real and measurable as velocity-based time dilation. Think back to the equivalence principle. Being in a gravitational field is equivalent to being in an accelerating reference frame. And we know from special relativity that accelerating observers experience time dilation. Put these together. Gravity must cause time dilation. Einstein made this argument more rigorous using the principle of general covariance and the requirement that his theory reduce to special relativity in the absence of gravity. The result? The stronger the gravitational field, the slower time passes. Here's a way to visualize it. Imagine two observers, one standing on the ground, one hovering at some height above the ground. They each have identical clocks. The person on the ground is deeper in Earth's gravitational field, closer to the center, where space-time is more curved. The person higher up is in a weaker field, farther from the center, where space-time is less curved. General relativity predicts that the clock on the ground runs slower than the clock higher up. From the perspective of the person higher up, they see the ground-level clock ticking slower. From the perspective of the person on the ground, if they could observe the higher clock, they'd see it ticking faster. This isn't an illusion or an artifact of signal delay. If both people meet up after some time, they'll find that the ground-level clock really has recorded less elapsed time. Time itself passed more slowly in the stronger gravitational field. The effect is tiny for Earth's gravity. Go up a mountain just a few kilometers higher, and your clock runs faster by about 10 nanoseconds per day compared to sea level. Completely unmeasurable without atomic clocks. But we can measure it. In 1971, physicists Joseph Hathele and Richard Keating flew atomic clocks around the world on commercial airplanes and compared them to atomic clocks that stayed on the ground. The flying clocks were affected by both velocity time dilation, they were moving, so special relativity says their clocks should run slow, and gravitational time dilation. They were at higher altitude, so general relativity says their clocks should run fast. Both effects were predicted, calculated, and measured. The gravitational effect and the velocity effect partially cancelled, but not completely. The final result matched Einstein's predictions. The clocks really did show different elapsed times, exactly as relativity predicted. More modern experiments are even more precise. In 2010, researchers at NIST, National Institute of Standards and Technology, measured gravitational time dilation over a height difference of just 33 centimeters, about a foot. They could detect that a clock on a shelf runs faster than a clock on the floor. The effect was about 90 billionths of a second per day, but they measured it. This isn't just a physics curiosity. GPS satellites have to account for gravitational time dilation. The satellites orbit at about 20,000 kilometers altitude, where Earth's gravitational field is weaker than at the surface. Clocks on the satellites run faster than clocks on the ground by about 45 microseconds per day due to gravitational time dilation. There's also a velocity effect. The satellites are moving fast, so special relativistic time dilation makes their clocks run slow by about 7 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds per day compared to ground clocks. If we didn't correct for this, GPS would accumulate errors of about 10 kilometers per day. Your phone's navigation would be useless. The fact that GPS works is direct practical proof that general relativity correctly describes how gravity affects time. Gravitational time dilation also explains gravitational redshift. Light climbing out of a gravitational well gets redshifted. Its wavelength increases, its frequency decreases. This isn't because the light is losing energy climbing against gravity, though you can think of it that way. It's because time itself runs at different rates at different heights. Imagine a laser on the ground emitting light with a specific frequency, say 1 oscillation per second as measured by a ground-level clock. This light travels up to a higher altitude where clocks run faster. An observer at altitude receives this light, but their clock is ticking faster than the ground clock, so they measure fewer than 1 oscillation per second. The frequency appears lower. The light is redshifted. This has been measured. The Pound-Rebka experiment in 1959 measured gravitational redshift over a height difference of just 22.5 meters in a tower at Harvard. They detected a frequency shift of about 1 part in 10 circumflex 15, exactly as predicted. Near more massive objects, gravitational time dilation becomes extreme. Near a neutron star, time runs noticeably slower. Near a black hole, the effect becomes dramatic. Here's something wild. You could orbit close to a black hole, experiencing strong time dilation, then return to Earth and find that decades or centuries have passed, while you aged only years. This isn't just a theoretical possibility. This is what the mathematics of general relativity predicts. The movie Interstellar actually got this right. The scene where they visit a planet near a black hole and experience severe time dilation. That's real physics. Gravitational time dilation has profound implications. It means time is not universal. Time is local. Your time depends on where you are in the gravitational field. Two people at different altitudes literally experience time passing at different rates, And this raises deep questions about the nature of time. Is time a fundamental feature of reality, or is it emergent from something more basic? If time can be dilated by both motion and gravity, if it can pass at different rates in different locations, what is time really? We don't have answers to these questions yet, but we know the effect is real. Gravity bends time just as surely as it bends space. And when gravity becomes extreme, when you have enough mass compressed into a small enough region, the bending becomes so severe that something breaks. That something is a black hole. And black holes are where our understanding of space-time reaches its limits. Black holes are where general relativity makes its most extreme predictions. They're regions where space-time curvature becomes so intense that weird, counterintuitive, and frankly disturbing things happen. They're also predictions that Einstein himself didn't believe could actually exist in nature. The first black hole solution was found in 1916, less than a year after Einstein published the field equations. Karl Schwarzschild, a German physicist serving in the army during World War I, derived an exact solution for the space-time geometry around a perfectly spherical, non-rotating mass. Remarkably, he did this while fighting on the Russian front. He sent the solution to Einstein, who was impressed but also troubled by its implications. The Schwarzschild solution revealed something strange. There's a critical radius around any mass where something dramatic happens. This radius is now called the Schwarzschild radius or the event horizon. For an object with the Sun's mass, this radius is about 3 kilometers. For Earth's mass, it's about 9 millimeters. Normal objects like the Sun and Earth are much larger than their Schwarzschild radii, so this critical surface is buried deep inside them. Nothing weird happens. But if you could somehow compress the Sun down to a sphere 3 kilometers in radius, or compress Earth down to the size of a marble, something extraordinary would occur. At the Schwarzschild radius, time dilation becomes infinite. A clock at that radius appears to an outside observer to stop ticking. Light emitted from that radius gets infinitely redshifted, and anything that crosses inside that radius can never come back out. Never. Not even light. This is what we mean by a black hole. It's not really a hole, and it's not really black in the sense of being a dark object. It's a region of space-time where gravity is so strong that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. The event horizon is the point of no return. Once you cross it, all your possible future paths through space-time lead deeper into the black hole. You cannot escape any more than you can escape moving forward through time. The future direction in space-time literally points inward toward the singularity. Speaking of which, inside the black hole, at the center, the Schwarzschild solution predicts a singularity, a point where space-time curvature becomes infinite. The equations blow up. Densities become infinite. Tidal forces become infinite. Our mathematical description breaks down completely. Einstein found this disturbing. He thought singularities indicated that the theory was breaking down, that real physical objects couldn't actually collapse past their Schwarzschild radius. Surely something would stop the collapse before a singularity formed. Many physicists agreed. Even when Robert Oppenheimer and others showed in the 1930s that massive stars could collapse into black holes after exhausting their nuclear fuel, most scientists thought this was a mathematical pathology rather than a physical prediction. Real stars, they thought, would find some way to avoid this fate. They were wrong. We now have overwhelming evidence that black holes exist. We've observed stars orbiting invisible massive objects at the centers of galaxies. We've detected X-rays from matter spiraling into compact objects, too massive to be anything but black holes. We've even photographed the shadow of a supermassive black hole. The Event Horizon Telescope image of M87's black hole, released in 2019, showed a dark region surrounded by glowing matter, exactly as predicted. And in 2015, LIGO detected gravitational waves from two black holes merging. ripples in space-time from two black holes orbiting each other, spiraling inward and crashing together. The signal matched the predictions of general relativity perfectly. Black holes are real, but they're still deeply mysterious. What happens at the singularity? General relativity predicts infinite curvature, but infinity usually means your theory is breaking down. We expect quantum effects to become important at extremely small scales and high densities, but we don't have a theory of quantum gravity to describe what actually happens. Does the singularity really exist, or does quantum mechanics somehow prevent it? Is there a bounce where the collapse reverses? Does the singularity connect to another region of space-time, creating a wormhole? We don't know. We can't observe inside a black hole because information can't escape. There's also the puzzle of what happens from the perspective of someone falling in. From far away, you'd see them slow down as they approach the event horizon, getting redder and dimmer, appearing to freeze at the horizon, but never quite crossing it. This is due to gravitational time dilation. Time at the horizon appears stopped from outside, but from the perspective of the person falling in, nothing special happens at the horizon. They cross it in finite time by their own clock. They might not even notice when it happens. For a supermassive black hole, the tidal forces at the horizon can be tiny. They'd only realize they'd crossed when they tried to turn around and couldn't. After crossing, they'd inevitably hit the singularity. The tidal forces, the difference in gravitational pull between their head and feet, would grow rapidly. Long before reaching the singularity, they'd be torn apart by these forces, stretched like spaghetti. Physicists call this spaghettification, which is either the best or worst technical term ever coined. Different reference frames give wildly different descriptions of the same event. Outside observers see the infalling person frozen at the horizon forever. The infalling person crosses in finite time and hits the singularity. Both descriptions are valid from their respective frames. This is relativity taken to the extreme. Black holes also raise paradoxes we'll get to later. They seem to destroy information, violating quantum mechanics. They might emit radiation and evaporate, creating even more puzzles. They might be gateways to other universes or other times. They definitely represent the limits of our current understanding. What's clear is that black holes are real. They're predictions of general relativity that have been confirmed observationally, and they represent regions where space-time itself behaves in ways that seem to break our normal intuitions about space, time, and causality. They're also places where our current theory, general relativity, meets its match. The theory predicts its own breakdown at singularities. It tells us there should be a point where curvature becomes infinite, and at that point, the theory can no longer make predictions. We need a deeper theory, probably a quantum theory of gravity, to understand what's really happening. But until we have that theory, black holes remain one of the most fascinating and disturbing predictions of Einstein's geometric view of gravity. They're ultimate proof that space-time can be curved, twisted, and broken in ways that defy imagination. And they're just one of the strange phenomena that emerge when you take general relativity seriously. In the 1970s, Stephen Hawking made a discovery that shocked the physics community. He showed that black holes aren't completely black. They emit radiation, they glow, and eventually, they evaporate completely. This discovery created what might be the deepest puzzle in theoretical physics, the black hole information paradox, and it's directly related to our understanding of space-time. Here's how Hawking's discovery works. In quantum field theory, empty space isn't really empty. It's filled with quantum fluctuations, particle-antiparticle pairs constantly popping into existence and annihilating each other. Normally, these virtual particles exist for such a short time that they have no lasting effect. But near a black hole's event horizon, something different can happen. A particle-antiparticle pair can form just outside the horizon. One particle falls into the black hole. The other escapes to infinity. From far away, it looks like the black hole emitted a particle. Where does the energy for this real particle come from? from the black hole's gravitational field. The particle that fell in had negative energy relative to infinity, so the black hole loses mass. The escaping particle carries away positive energy. The black hole shrinks. This radiation is called Hawking radiation. The black hole glows with a thermal spectrum, like a hot object. The smaller the black hole, the hotter it is and the faster it radiates. A solar mass black hole would have a temperature of about 60 nanokelvins, far too cold to detect above the cosmic microwave background. But a smaller black hole would be hotter. Eventually, the black hole evaporates completely. All its mass is converted into radiation and escapes. The black hole disappears. Now here's the problem. Imagine you throw a book into a black hole. The book contains information, the arrangement of letters on its pages, the molecular structure of the paper and ink, the quantum states of all its particles. That information falls past the event horizon and, according to general relativity, hits the singularity and is destroyed. Fine, you might think. The information is gone. But quantum mechanics says information cannot be destroyed. This isn't just a principle. It's a consequence of the fundamental equations of quantum mechanics being reversible. Given the quantum state of a system at one time, you can in principle calculate its state at any other time, forward or backward. Information is preserved. So, what happens to the information in the book? It's trapped inside the black hole, but the black hole eventually evaporates. Does the information come back out in the Hawking radiation? Hawking's calculations suggested no. The radiation is purely thermal. It depends only on the black hole's mass, not on what fell in. A black hole formed from collapsing matter would emit the same radiation as a black hole formed from antimatter, or photons, or books. The information about what fell in seems to be lost forever. This violates quantum mechanics. You'd have a process, throwing something into a black hole and waiting for it to evaporate. That destroys information. That creates a pure state, the thing you threw in, into a mixed state, thermal radiation. This shouldn't be possible in quantum mechanics. This is the information paradox. General relativity says the information is destroyed at the singularity, or lost in the evaporation. Quantum mechanics says information must be preserved. Both can't be right. Physicists have debated this for nearly 50 years. Some argued that information does come out in subtle correlations in the Hawking radiation that Hawking's calculation missed. But how? The radiation is generated at the horizon, which is causally disconnected from the interior where the information fell. How could the radiation know about the information inside? Others suggested that information is destroyed, and quantum mechanics must be modified for systems involving gravity and black holes. But this seems drastic. Quantum mechanics is one of our most successful theories. Some proposed that information is preserved in remnants, stable particles left over after a black hole evaporates. But these would need to have enormous, possibly infinite, internal states to encode all the information that ever fell into black holes of that mass. This seems bizarre. Hawking himself eventually changed his mind and argued that information is preserved, though he never gave a fully satisfactory mechanism. He proposed that information is stored at the event horizon in some way and is released during evaporation. More recently, ideas from string theory and holography suggest that information might be encoded on the event horizon in a kind of holographic layer. The three-dimensional interior of the black hole might be completely described by information on its two-dimensional surface. When the black hole evaporates, this surface information is released in the radiation. There's also the firewall paradox, which we'll discuss later. If information must escape in the radiation, and if that radiation is entangled with the interior of the black hole, then quantum mechanics requires that there be a high-energy firewall at the event horizon. But this violates the equivalence principle, which says nothing special should happen at the horizon. The information paradox remains unsolved. We don't have a complete agreed-upon answer. Different approaches, string theory, loop quantum gravity, other approaches suggest different resolutions, but none is definitive. What's clear is that the paradox represents a fundamental tension between general relativity and quantum mechanics. It's telling us that our current understanding is incomplete. We're missing something deep about how space-time, gravity, and quantum mechanics fit together. The paradox also suggests that black holes are more than just predictions of general relativity. They're laboratories for testing the limits of our theories. They're places where space-time curvature is so extreme that quantum effects can't be ignored, where we need a quantum theory of gravity to make sense of what's happening. And they're a hint that space-time itself might not be fundamental. If information is preserved, and if it's encoded holographically on horizons, then maybe the three-dimensional geometry of space-time is somehow emergent from more basic quantum information. Maybe space-time is a kind of illusion, a useful approximation that breaks down in extreme conditions, like black hole interiors. These are speculative ideas, and we don't know which, if any, are correct. But the information paradox has pushed physicists to question the very foundations of space-time. It's forced us to confront the possibility that Einstein's beautiful geometric picture of gravity, as successful as it's been, is not the final answer. Black holes are where general relativity meets its limits, and the information paradox is where we're forced to admit that we still don't fully understand space-time, even a century after Einstein's breakthrough. In 1935, Einstein and his colleague Nathan Rosen were studying the mathematical structure of black holes when they discovered something unexpected in the equations. The Schwarzschild solution, the geometry of space-time around a black hole, had a strange feature that they hadn't noticed before. The black hole geometry doesn't just describe one region of space, it actually connects two separate regions of space-time. There's a bridge, a tunnel through space-time, connecting what could be two different universes, or two distant parts of the same universe. This bridge is now called an Einstein-Rosen bridge, or more popularly, a wormhole. Here's how it works mathematically. The Schwarzschild solution describes a black hole, but if you extend the geometry fully, if you look at the complete mathematical structure, you find that there's not just one event horizon, but two, one in each of two separate space-time regions. And these two regions are connected by a throat, a tunnel through space-time. Imagine space-time as a flat sheet. Now imagine poking two holes in the sheet and connecting them with a tube. That tube is the wormhole, a shortcut connecting distant regions. If you could enter one mouth of the wormhole, you'd travel through the throat and emerge at the other mouth, potentially light years away from where you started. This sounds like science fiction, and in a sense it is, because there's a critical problem. The Einstein-Rosen bridge isn't traversable. The geometry is such that the throat pinches off before anything can get through. Any particle or light beam that enters one mouth gets crushed at the throat before it can reach the other mouth. The connection exists mathematically, but you can't actually use it as a shortcut. To understand why, think about the dynamics. The wormhole throat is a region of extreme curvature. In the original Einstein-Rosen bridge, this throat is collapsing. Space-time is pinching off. Any signal sent in would get caught in the collapse and destroyed. The throat closes faster than light can cross it. But physicists asked, could you hold a wormhole open? Could you prop up the throat somehow so that things could actually pass through? The answer is maybe, but it requires something exotic, negative energy, or more precisely, matter or fields that violate what's called the null energy condition, the requirement that energy density plus pressure is always positive for any observer moving at the speed of light. In normal matter, this condition is satisfied. Ordinary matter, radiation, electromagnetic fields, they all have positive energy density. But general relativity doesn't absolutely forbid negative energy. Quantum field theory even provides some situations where localized negative energy can exist, at least temporarily, through something called the Casimir effect. If you could somehow gather enough exotic matter with negative energy and position it in the throat of a wormhole, you might be able to hold the throat open. The negative energy would push outward, counteracting the tendency of space-time to collapse, keeping the wormhole traversable. How much exotic matter would you need? Calculations suggest an absurd amount. To keep a wormhole 1 meter across open, you'd need negative energy equivalent to the total mass energy of Jupiter. And we don't know how to create or concentrate negative energy on anything remotely approaching that scale. Even if you could create a traversable wormhole, there are other problems. Kip Thorne and others showed that if you have a traversable wormhole, you can potentially use it to create a time machine. Move one mouth of the wormhole at high speed and then bring it back. Time dilation means less time has passed for the moving mouth. Now you have 2 mouths at the same location but at different times. Enter 1. Emerge from the other in the past. This raises all the classic time travel paradoxes. Could you go back and prevent your younger self from entering the wormhole? Most physicists suspect that either traversable wormholes are impossible or there's some mechanism, perhaps quantum effects, that prevents using them for time travel. Hawking proposed a chronology protection conjecture, the idea that the laws of physics prevent the creation of time machines. Maybe vacuum fluctuations build up infinite energy when you try to create closed time-like curves, destroying the wormhole before you can use it for time travel. So, are wormholes real? The short answer is, we don't know. They're allowed by the equations of general relativity under certain conditions, but those conditions require exotic matter that probably doesn't exist in the required quantities. We've never observed a wormhole. We have no evidence that they exist in nature. Some physicists speculate that wormholes might have existed in the very early universe, during the Big Bang, when energy densities and curvatures were extreme. If so, tiny primordial wormholes might be scattered through space, but they'd likely be microscopic and extremely unstable. There's also a newer idea, which we'll discuss later, that quantum entanglement and wormholes might be related. The EPR conjecture suggests that when 2 particles are entangled, they might be connected by a non-traversable wormhole. This would be a radical reinterpretation of what entanglement means and what space-time is. But for now, traversable wormholes remain in the realm of speculation and science fiction. They're consistent with general relativity under certain extreme conditions, but those conditions are likely impossible to achieve. They represent another way that the mathematics of curved space-time predicts bizarre possibilities that may or may not correspond to physical reality. What we do know is that space-time can be curved in ways that create shortcuts, connections, and topologies far more complex than the simple flat space we intuitively imagine. Whether those exotic topologies actually exist in our universe is an open question. And speaking of exotic space-time behavior, there's something even more surprising that general relativity predicts, something that Einstein himself initially rejected as absurd. The universe itself can expand or contract. Space-time isn't static. It can evolve dynamically on cosmic scales. When Einstein first developed general relativity, he assumed the universe was static, unchanging on the largest scales, eternal and stable. This seemed obvious. Yes, stars and planets move, but the overall structure of the universe should be constant, right? So Einstein was disturbed when he tried to find a solution to his field equations that described a static universe, and couldn't do it. His equations kept predicting that the universe should be either expanding or contracting. A static universe wasn't a natural solution. This bothered Einstein so much that in 1917 he modified his own equations. He added a term called the cosmological constant, essentially a form of energy built into the fabric of space-time itself, and tuned it precisely to counteract gravitational attraction and hold the universe static. But the static solution was unstable. Any small perturbation would cause it to start expanding or contracting. It was like balancing a pencil on its point. Theoretically possible, but not realistic. Then, in the 1920s, Alexander Friedmann and Georges Lemaitre independently found solutions to Einstein's original equations without the cosmological constant that described expanding or contracting universes. These weren't just mathematical curiosities, they were valid, stable solutions that seemed to describe realistic cosmologies. Einstein was skeptical. An expanding universe seemed bizarre. But then came the observations. In the 1920s, Edwin Hubble was using the Mount Wilson Observatory to study distant galaxies. He was measuring their distances and their velocities, how fast they were moving toward or away from us. The velocities came from measuring redshift, the shift in spectral lines toward longer wavelengths, indicating motion away from us. What Hubble found was shocking. Nearly all galaxies were moving away from us. And not just that. The farther away a galaxy was, the faster it was receding. There was a linear relationship. Velocity equals distance times a constant. This constant is now called the Hubble constant. Imagine dots on the surface of a balloon. Now inflate the balloon. Every dot moves away from every other dot, and dots that are farther apart move away from each other faster. That's what Hubble was seeing. The universe was like an inflating balloon. This wasn't galaxies moving through space. This was space itself expanding. The distances between galaxies were increasing because new space was being created between them. Space-time itself was stretching. Einstein reportedly called adding the cosmological constant his biggest blunder. His original equations had predicted the expansion of the universe, and he'd modified them because he didn't believe it. If he'd trusted his equations, he could have predicted cosmic expansion before it was observed. The expanding universe explained something else too, Olber's paradox. If the universe is infinite, eternal and static, filled with stars, why is the night sky dark? Light from infinite stars should make the sky blazingly bright. But if the universe is expanding and had a beginning, there's only been a finite time for light to reach us from a finite region. The night sky is dark because we can only see a limited portion of the universe. The expansion also means the universe had a beginning. If galaxies are moving apart now, then in the past they must have been closer together. Extrapolate backward, and you reach a point where all the matter and energy in the universe was compressed into an infinitely small, infinitely dense state, a singularity. The beginning of space-time itself. This is the Big Bang. Though that name is misleading, it wasn't an explosion in space, it was the expansion of space itself from an initial state. Now you might wonder, if space is expanding, are we expanding too? Are atoms expanding? Are galaxies expanding? No. Objects held together by forces, electromagnetic forces in atoms, gravitational forces in galaxies, don't expand. The expansion of space only affects the distance between objects that aren't gravitationally bound to each other. Within our galaxy, gravity overwhelms the expansion. Within our local group of galaxies, same thing. It's only on scales of hundreds of millions of light years between galaxy clusters that expansion dominates. The rate of expansion is described by the Hubble constant. Current measurements put it around 70 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light years of distance, space is expanding at an additional 70 kilometers per second. This seems fast, but on small scales it's negligible. Over the distance from Earth to the Sun, space is expanding at about 1 centimeter per year, completely overwhelmed by other effects. The expanding universe also has a horizon. Because space is expanding, there are galaxies so far away that their light has never had time to reach us. There's a cosmic horizon, analogous to the event horizon of a black hole, beyond which we cannot see. This horizon is currently about 46 billion light-years away, even though the universe is only 13.8 billion years old, because space has been expanding the whole time. And there's something even stranger. When astronomers measured the expansion rate more carefully in the 1990s, looking at distant supernovae, They expected to find that the expansion was slowing down. Gravity should be pulling galaxies together, decelerating the expansion. Instead, they found the expansion is accelerating. The universe is expanding faster and faster. Something is pushing space-time apart, overwhelming gravity on cosmic scales. Something that acts like a negative pressure, like Einstein's cosmological constant. They called it dark energy, and it's one of the biggest mysteries in physics. If the universe is expanding now, then in the past it was smaller. Galaxies were closer together. Space itself was more compressed. Go back far enough, and you reach a point where all the matter and energy in the observable universe was concentrated in an incredibly hot, dense state. Go back even further, and general relativity predicts a singularity, a point where density and temperature become infinite, where space-time curvature becomes infinite, where the equations break down completely. This is the Big Bang. But the Big Bang wasn't an explosion in space. It wasn't like a bomb going off in an empty room. It was the beginning of space itself and time itself. There was no before the Big Bang in any meaningful sense, because time didn't exist before space-time began. This is hard to wrap your mind around. We're used to thinking of the universe as existing in space and time, but general relativity says that space and time are part of the universe, not a container it sits in. When the universe began, space-time began with it. Imagine the surface of a sphere, say Earth. Now ask, what's north of the North Pole? The question doesn't make sense. North is a direction on Earth's surface, and the North Pole is as far north as you can go. There is no north of the North Pole. Similarly, asking what happened before the Big Bang might not make sense. Before is a time concept, and time began with the Big Bang. There may be no before, just as there's no north of the North Pole. Of course, this is applying general relativity to a domain where it probably breaks down. Near the Big Bang singularity, densities and temperatures were so extreme that quantum effects surely mattered. We need a quantum theory of gravity to describe what really happened. General relativity alone can't tell us. Some quantum gravity theories suggest the Big Bang wasn't actually a singularity, but a bounce from a previous contracting phase. Others suggest the universe emerged from quantum fluctuations in some pre-existing quantum state. We don't know. The very beginning of the universe is still mysterious, but we can trace the expansion back to very early times with reasonable confidence. About 1 second after the Big Bang, the universe was hot enough for nuclear fusion to occur everywhere. Protons and neutrons combined to form the first atomic nuclei, mostly hydrogen and helium. The ratio of hydrogen to helium we observe in the universe today matches what we calculate should have formed in the first few minutes. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with nuclei to form neutral atoms. Before this, the universe was a plasma. Electrons and nuclei were separated, and photons couldn't travel far without scattering off free electrons. The universe was opaque, but when atoms formed, photons could suddenly travel freely. The universe became transparent. The light from this moment, redshifted by cosmic expansion to microwave wavelengths, is what we observe today as the cosmic microwave background. It's our earliest direct view of the universe. The Big Bang theory also explains the abundances of elements we observe. Why is the universe about 75% hydrogen and 25% helium by mass, with only trace amounts of heavier elements? Because that's what formed in the first few minutes. Heavier elements were cooked later in stars. It explains why the universe looks roughly the same in all directions. It expanded from a small, roughly uniform initial state. It explains the cosmic microwave background radiation. It explains Hubble's observation of galactic redshifts. Multiple independent lines of evidence all point to the same picture. But the Big Bang theory also raises profound questions. Why did the Big Bang happen? What caused it? What, if anything, existed before it? Is our universe unique, or are there others? We don't have answers. We can trace cosmic history back to fractions of a second after the Big Bang using known physics. But the very beginning, what initiated the expansion, what happened at or before the singularity, that's still beyond our current understanding. Some physicists think these questions might not even be meaningful. If time itself began at the Big Bang, asking what caused it is like asking what's north of the North Pole. The question assumes a temporal framework that doesn't exist. Others think there must be more to the story, some quantum process or pre-Big Bang state that we haven't discovered yet. Various theories propose different answers: eternal inflation, cyclic universes, quantum tunneling from nothing, multiverses. But these are speculative. We don't have evidence for any particular scenario. What we do know is that general relativity, combined with observations of the expanding universe, tells us that space-time itself had a beginning. The universe hasn't always existed in its current form. It was born, it evolved, and it continues to evolve today. And that evolution has taken a strange turn. Not only is the universe expanding, but the expansion is speeding up. Something is pushing space-time apart. Something we don't understand at all. In 1998, two independent teams of astronomers were studying distant supernovae, specifically type Ar supernovae, which are extremely bright and have a consistent peak luminosity. This makes them standard candles, objects whose actual brightness we know, so we can calculate their distance by measuring how bright they appear. These teams were measuring the distances to supernovae in distant galaxies and comparing those distances to the galaxy's redshifts, which tells us how fast they're receding. The goal was to measure how much the cosmic expansion had been decelerating over time. Everyone expected the expansion to be slowing down because gravity pulls everything together. The results shocked everyone. The expansion wasn't slowing down. It was speeding up. Distant galaxies were farther away than they should be if the expansion had been constant or decelerating. The universe's expansion had been accelerating for the past several billion years. This made no sense in terms of ordinary matter and energy. Gravity is attractive. Everything we know about, stars, planets, gas, dark matter, radiation, all of it pulls on everything else through gravity. This should slow the expansion down, not speed it up. But the observations were clear. Multiple studies confirmed it. In 1998, the Nobel Prize in Physics was awarded for this discovery. The universe really is expanding faster and faster. To explain this, physicists invoked something they called dark energy. Dark because we can't see it directly. We only infer it from its gravitational effects. Energy because it fills space with energy density. But dark energy has bizarre properties. It doesn't clump or cluster like matter. It doesn't dilute as space expands. It seems to have constant density everywhere in space, and that density stays constant even as space expands and creates more volume. It also has negative pressure. It pushes rather than pulls. In Einstein's equations, negative pressure causes repulsive gravity. Remember, the stress-energy tensor includes not just mass and energy density, but also pressure. Normal matter has positive pressure, which gravitationally attracts, though the effect is usually small. But something with negative pressure gravitationally repels. Dark energy acts like Einstein's cosmological constant, the term he added to his equations to keep the universe static, then removed when the expansion was discovered. Ironically, the cosmological constant might have been right all along, just for the wrong reasons. It doesn't hold the universe static. It causes accelerating expansion. How much dark energy is there? Measurements suggest it makes up about 68% of the total energy content of the universe. Ordinary matter, atoms, stars, planets, us, makes up less than 5%. Dark matter, another mystery we don't fully understand, makes up about 27%. Dark energy dominates. and we have no idea what it is. The simplest explanation is that it's vacuum energy, energy inherent to empty space itself. Quantum field theory predicts that the vacuum isn't actually empty, it's filled with quantum fluctuations, virtual particles popping in and out of existence. This vacuum should have an energy density, but when you calculate what that energy density should be, using quantum field theory, you get an answer that's wrong by a factor of 10 circumflex 120. That's 1 followed by 120 zeros. It's arguably the worst prediction in the history of physics. Maybe the calculation is wrong. Maybe the vacuum energy is exactly zero due to some symmetry we don't understand, and dark energy is something else entirely. But what? Some theories propose it's a new field filling space, sometimes called quintessence. This field would have properties similar to the cosmological constant, but might vary in time or space. Others suggest it's a modification of gravity itself. Maybe Einstein's equations need correction on cosmological scales. We've tried to measure whether dark energy's density changes over time. So far, it looks constant, consistent with a cosmological constant. But measurements aren't precise enough to rule out small variations. The existence of dark energy has profound implications for the universe's future. If it continues to dominate, the expansion will keep accelerating. Distant galaxies will recede faster and faster. Eventually, galaxies outside our local group will be moving away faster than light, not violating relativity. Space itself is expanding faster than light can cross it. They'll disappear beyond our cosmic horizon. In the far future, trillions of years from now, the night sky will be nearly empty. Only the local cluster of gravitationally bound galaxies will remain visible. Everything else will have been carried beyond the horizon by expansion. Future astronomers might not even be able to tell the universe is expanding, because there won't be distant galaxies to measure redshifts from. If dark energy's density increases over time, things get worse. In a scenario called the Big Rip, the acceleration becomes so extreme that it eventually overcomes gravity on all scales. Galaxy clusters get torn apart, then galaxies, then solar systems, then planets, then atoms themselves. Space-time gets ripped to shreds. If dark energy's density decreases, the expansion might eventually reverse. The universe could stop expanding and start contracting, leading to a big crunch, the opposite of the Big Bang, where everything collapses back into a singularity. We don't know which scenario is correct because we don't know what dark energy is. It's the biggest mystery in cosmology. We can measure its effects, the accelerating expansion, but we have no confirmed explanation for what causes it. Some physicists suspect dark energy is telling us that our understanding of space-time on cosmic scales is incomplete. Maybe general relativity breaks down at cosmological distances. Maybe space-time has properties we haven't discovered. Maybe the entire framework of geometry and gravity needs revision. Or maybe there's a simpler explanation we just haven't thought of yet. Einstein's cosmological constant, vacuum energy, might be the right answer, and we just need to understand why its value is what it is. For now, dark energy remains one of the deepest puzzles about space-time. We know it's there. We know it's causing the universe to expand faster and faster. We know it dominates the universe's energy content. But we don't know what it is, why it exists, or what it means for the fundamental nature of reality. And dark energy isn't the only recent surprise about space-time. In 2015, we finally detected something Einstein predicted a century earlier but thought might be too faint to ever observe: gravitational waves. Einstein predicted gravitational waves in 1916, just a year after publishing general relativity. The reasoning was straightforward. If space-time is a dynamic physical thing that can be curved, then disturbances in space-time should propagate like waves. Just as accelerating electric charges create electromagnetic waves, accelerating masses should create gravitational waves, ripples in the fabric of space-time itself. But Einstein thought we'd never detect them. Gravitational waves are extraordinarily weak. Even cataclysmic cosmic events produce waves that barely disturb spacetime by the time they reach Earth. Einstein calculated that the effects would be so tiny as to be unmeasurable. He was almost right. Detecting gravitational waves required some of the most sensitive instruments ever built, searching for decades before finding anything. But on September 14, 2015, the LIGO detectors, two massive instruments in Louisiana and Washington, detected something. A gravitational wave had passed through Earth. The detectors measured it, and from the signal's shape, scientists could tell what had caused it. Two black holes, each about 30 times the mass of the Sun, spiraling into each other and merging 1.3 billion light-years away. The collision had released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. And yet, by the time the wave reached Earth, it stretched and compressed space by less than 1,000th the width of a proton. LIGO detected this. It measured space-time itself vibrating as the wave passed through. Let me explain how gravitational waves work. Imagine two black holes orbiting each other. They're moving through curved space-time, following geodesics, but their motion disturbs the space-time around them. These disturbances propagate outward at the speed of light as waves. What does a gravitational wave do? It alternately stretches and compresses space in perpendicular directions. As the wave passes through, space expands in one direction and contracts in the perpendicular direction. Then the pattern reverses. It's a quadrupole oscillation. Unlike light waves, which can oscillate in any direction, gravitational waves have a specific pattern of stretching and squeezing. LIGO detects this by using laser interferometry. Each detector has two arms, each 4 kilometers long, perpendicular to each other. A laser beam is split and sent down both arms, bouncing off mirrors at the ends. The beams recombine and interfere. If a gravitational wave passes through, it stretches one arm while compressing the other. The laser beams travel slightly different distances. When they recombine, the interference pattern changes. By measuring this change, LIGO can detect the gravitational wave. The sensitivity required is absurd. LIGO needs to measure changes in arm length of about 10 circumflex 18 meters, 1,000th the width of a proton. Every possible source of noise has to be eliminated or accounted for: seismic vibrations, thermal fluctuations, quantum uncertainty and photon arrival times, even the gravity of clouds passing overhead. The engineering is extraordinary. The September 2015 detection was so clear, so obvious, that the LIGO team initially thought it might be a test signal someone had injected for calibration. But it was real. They spent months verifying, checking, ruling out every possible source of error. In February 2016, they announced the detection publicly. Since then, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Most are merging black holes, but they've also detected merging neutron stars. The neutron-star merger was particularly exciting because it was observed in both gravitational waves and electromagnetic radiation, a true multi-messenger astronomy event. These detections have confirmed general relativity's predictions about gravitational waves in exquisite detail. The waveforms match theoretical calculations. The waves travel at the speed of light, as predicted. The energy carried by the waves matches what you'd expect from the masses and spins of the merging objects. We've also learned things we couldn't have discovered any other way. We've measured the masses and spins of black holes throughout the universe. We've confirmed that black hole mergers happen and that they release tremendous energy. We've tested general relativity in the strong field regime, regions of extreme space-time curvature where we'd never been able to test it before. Gravitational wave astronomy is a new window on the universe. Electromagnetic telescopes see light. They observe charged particles and atoms. But most of the universe is dark and doesn't emit light. Gravitational wave detectors see mass and energy itself through their effects on spacetime geometry. We can observe black holes directly through their gravitational waves. We can detect neutron star collisions that might be too far away or too obscured by dust to see in light. We might even be able to detect gravitational waves from the Big Bang itself, from the very early universe when it was too hot and dense for light to escape. The detection of gravitational waves is also profound confirmation that spacetime is real. It's not just a mathematical abstraction or a convenient way of describing gravity. It's a physical thing that can vibrate, oscillate, carry energy, produce measurable effects. Spacetime is as real as the ground beneath your feet, and gravitational waves reveal something else. Spacetime has dynamics. It doesn't just sit there, curved by matter. It responds, evolves, propagates disturbances. It's an active, dynamic medium, not a passive stage. This raises deep questions. If space-time can oscillate and carry waves, what is it made of? Is there some underlying structure, some granularity or discreteness to space-time itself? Can space-time break or tear? What happens at the smallest scales? We don't have answers yet. But gravitational waves give us a new tool to probe these questions, and they've confirmed beyond any doubt that Einstein was right. Space-time is not just curved. It can ripple. There's another effect of curved, rotating space-time that's equally bizarre and was confirmed even more recently: frame dragging. When you think about a rotating object in space, say a spinning planet, you probably imagine it rotating relative to some background of fixed space. The planet spins, but space itself stays still, not in general relativity. A rotating massive object doesn't just curve space-time around it, it drags space-time around with it. Space itself gets twisted into a rotating pattern. This is called frame dragging, or the lens-thirring effect. Imagine space-time as a viscous fluid, like honey. Now imagine spinning a massive ball in the honey. The honey near the ball gets dragged along, rotating with it. Honey farther away rotates more slowly. That's roughly what happens with space-time around a rotating mass. But it's not just an analogy. Space-time really does get twisted, and this has measurable effects. If you're in orbit around a rotating object, the orbital plane itself slowly rotates, precesses, because space-time is being dragged around. If you have a gyroscope in orbit, its axis of rotation slowly shifts, because the very definition of non-rotating, the inertial frame, is being dragged. Einstein and others predicted this effect in the early 1900s. But measuring it is incredibly difficult, because the effect is tiny. For Earth, which is rotating relatively slowly and has relatively weak gravity, the frame-dragging effect is measured in milliarc seconds per year. You need extraordinarily precise instruments orbiting for years to detect it. In 2004, NASA launched Gravity Probe B specifically to measure frame dragging around Earth. The satellite carried 4 gyroscopes, the most perfect spheres ever made, polished to within 40 atoms of perfect roundness. These gyroscopes were cooled to near absolute zero and suspended in a vacuum to eliminate any non-gravitational torques. The spacecraft orbited Earth for over a year, measuring how the gyroscope's axis shifted. The prediction from general relativity was that frame dragging would cause the gyroscope axes to precess by about 39 milliarc seconds per year. The analysis took years. The data was messy. There were unexpected torques from patches on the gyroscope surfaces, electromagnetic effects, all kinds of systematic errors to sort out. But eventually, after careful analysis, they confirmed it. The gyroscopes precessed by almost exactly the predicted amount. Frame dragging is real. This is mind-bending. Space-time near Earth isn't just curved, it's rotating. The very fabric of reality is being twisted around by Earth's rotation. What we call inertial frames, non-rotating reference frames, are themselves rotating relative to distant stars because local spacetime is rotating. The effect is much stronger near more rapidly rotating, more massive objects. Near a rotating black hole, a Kerr black hole, frame dragging becomes extreme. Close to the black hole, there's a region called the ergosphere where space-time is being dragged around so fast that nothing can remain stationary. Even light has to orbit in the direction of the black hole's rotation. Inside the ergosphere, it's impossible to stay still. You're dragged along with the rotating space-time, whether you like it or not. You can still escape the ergosphere. It's outside the event horizon, but you can't just hover there. You have to move, orbiting in the direction of rotation. Frame dragging also affects the event horizon of a rotating black hole. The horizon isn't spherical, it's oblate, bulging at the equator, and there's another surface outside it, called the outer horizon or ergosphere boundary, where frame dragging becomes significant. Rotating black holes can have bizarre properties because of frame dragging. You can, in principle, extract energy from a rotating black hole through the Penrose process, dropping something into the ergosphere in just the right way so that it splits, with one piece falling into the black hole and the other escaping with more energy than you started with. The extra energy comes from the black hole's rotation. There's even a possibility that frame dragging around rapidly rotating objects could close time-like curves, paths through space-time that loop back on themselves in time. These are solutions to Einstein's equations, but most physicists suspect they're unphysical, that some mechanism, probably quantum effects, prevents them from actually forming. What's clear is that frame dragging is yet another way that space-time is far weirder than our intuitions suggest. Not only does mass curve space, but rotation twists it. Space-time is dynamic, responsive, malleable. It's not a passive background, but an active participant in the physics. And this raises profound questions about the nature of rotation itself. In Newtonian physics, you can ask whether something is rotating relative to absolute space. In general relativity, there's no absolute space, but there is a local inertial frame defined by nearby matter and space-time curvature. Rotation becomes relative to the distribution of mass and energy in the universe. This connects to something called Mach's principle, the idea that local inertial frames are determined by the distribution of matter throughout the universe. General relativity incorporates aspects of this, but doesn't fully realize Mach's vision. The relationship between local space-time structure and global matter distribution is still not fully understood. What we do know is that frame dragging is real, it's been measured, and it's another confirmation that space-time is a dynamic, physical entity that responds to matter and energy in complex ways. And if we want to understand the early universe, the moments after the Big Bang when the entire observable universe was compressed into a tiny region, we need to look at the cosmic microwave background. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was a hot plasma. Free electrons scattered photons constantly, making the universe opaque. After this moment, photons could travel freely through the neutral gas. The universe became transparent. The light from this moment, the first light that could travel freely through space, is still traveling through the universe today, but it's been redshifted by cosmic expansion from visible light to microwave wavelengths. This is the cosmic microwave background radiation, or CMB. It's the oldest light we can see, a snapshot of the universe when it was only 380,000 years old. The CMB was predicted in the 1940s by George Gamow and others as a consequence of the Big Bang theory. If the universe was once hot and dense, it should have been filled with thermal radiation. As the universe expanded and cooled, this radiation should have been redshifted to lower temperatures. They predicted it should now be at a temperature of a few Kelvin. In 1964, Arno Penzias and Robert Wilson accidentally discovered the CMB while working on a radio antenna at Bell Labs. They found a persistent noise in their detector that they couldn't eliminate. It was coming from all directions in the sky, at microwave wavelengths, with a temperature of about 3 Kelvin. This was the CMB, and its discovery provided strong confirmation of the Big Bang theory. Since then, we've studied the CMB in exquisite detail. Satellites like COBE, WMAP, and Planck have mapped the temperature and polarization of the CMB across the entire sky with incredible precision. And this radiation tells us an enormous amount about space-time itself. First, the CMB is remarkably uniform. The temperature is the same in all directions to about 1 part in 100,000. This tells us the early universe was extremely homogeneous and isotropic, roughly the same everywhere and in all directions. This supports the idea that the universe is expanding uniformly from a compact, uniform initial state. But the CMB isn't perfectly uniform. There are tiny variations, fluctuations of about 1 part in 100,000 in temperature across different regions of the sky. These fluctuations are the seeds that grew into galaxies and galaxy clusters. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter, which increased the gravity further, eventually collapsing into galaxies and stars. By analyzing the pattern of these fluctuations, their size, distribution, and correlations, we can determine fundamental parameters about the universe. What's the average density of matter and energy? What's the geometry of space on large scales? How fast is the universe expanding? The CMB tells us that the spatial geometry of the universe is flat, or very close to it. In general relativity, space can be curved on cosmic scales. It could be positively curved, like the surface of a sphere. If you travel far enough in one direction, you'd eventually come back from the opposite direction. Or it could be negatively curved, like a saddle surface. Or it could be flat, like Euclidean space extending infinitely. The CMB fluctuations encode information about this curvature. The characteristic size of the fluctuations depends on the geometry. Measurements show that space is flat to within about 1%. This means the universe is either infinite or, if closed, it's far larger than the observable universe. The CMB also tells us about the composition of the universe. By analyzing the detailed pattern of fluctuations, we can determine how much ordinary matter, dark matter, and dark energy there is. Current measurements give about 5% ordinary matter, 27% dark matter, and 68% dark energy. The CMB is one of the primary sources of evidence for dark energy. The polarization of the CMB, the orientation of the light waves, carries even more information. Gravitational waves from the very early universe should have left a specific pattern in the CMB polarization, called B-mode polarization. Detecting this would give us a direct window into the first instance after the Big Bang, potentially confirming theories of cosmic inflation. So far, primordial B-mode polarization hasn't been definitively detected, though there have been tentative signals. But the search continues because detecting it would be revolutionary. It would tell us about quantum fluctuations in space-time itself during the first 10 circumflex 35 seconds after the Big Bang. The CMB is also our most direct evidence that the universe had a beginning and has been expanding. We can see the moment when the universe became transparent. We can trace cosmic history backward to that moment. Before that, the universe was opaque. We can't see further back with electromagnetic radiation. But the CMB suggests there was a before. The fluctuations in the CMB had to come from somewhere. The most likely explanation is quantum fluctuations in the very early universe, amplified by cosmic inflation, a period of exponentially rapid expansion in the first fraction of a second after the Big Bang. The CMB is a snapshot of space-time at a specific moment in its evolution, a moment when the universe was small, hot, dense, and almost perfectly uniform. It's our window into cosmic history. It tells us what the universe was like, how it evolved, and what it's made of, and it raises deep questions about what came before. If the CMB shows us the universe at 380,000 years old, what happened in those first 380,000 years? What happened in the first second, the first microsecond? What was the nature of space-time itself at those earliest moments? To answer these questions, we need to understand quantum effects in space-time. And this brings us to one of the deepest questions in physics: is space-time continuous, or is it made of discrete chunks? Everything we've discussed so far treats space-time as continuous, a smooth manifold that can be curved and stretched, but has no fundamental granularity or discreteness. You can zoom in arbitrarily far, and space-time is still smooth. But this assumption might be wrong. There are reasons to think that space-time itself might be quantized, that there's a smallest possible unit of space and time, below which the very concept of space-time breaks down. The key hint comes from combining quantum mechanics and general relativity. Quantum mechanics has a fundamental scale, called the Planck length, about 10 circumflex 35 meters. This is constructed from fundamental constants: the speed of light, the gravitational constant, and Planck's constant. It's the scale where quantum effects of gravity should become important. At the Planck length, the uncertainty principle says that measuring a distance requires concentrating enough energy in a small enough region that the energy density would create a black hole. You can't measure space-time at scales smaller than the Planck length without the measurement itself creating so much curvature that space-time breaks down. This suggests the Planck length might be a fundamental minimum scale for space-time. Below it, the concept of a smooth geometric space might not make sense. Various approaches to quantum gravity take this idea seriously. Loop quantum gravity, one of the leading approaches, explicitly treats space-time as discrete at the Planck scale. In this framework, space is composed of tiny loops, one-dimensional quantum objects, that link together to form a network. This network has a discrete structure, like atoms in a material, rather than being continuous. Volume and area in loop quantum gravity come in discrete units. There's a smallest possible volume, about 1 cubic Planck length, and a smallest possible area, about 1 square Planck length. You can't have half of the minimum area or volume. Space is quantized. This doesn't mean space is made of little cubes or pixels. The structure is more abstract. It's a quantum network of connections and relationships. But the key point is that it's discrete, not continuous. String theory, another approach to quantum gravity, also suggests space-time might not be fundamental. In string theory, what we perceive as particles are actually tiny vibrating strings. Space and time emerge from the collective behavior of these strings. At the Planck scale, the strings themselves replace space-time as the fundamental description. Some versions of string theory incorporate discrete structures too. D-branes, matrix theory, and other formulations suggest that space-time is emergent from more fundamental quantum degrees of freedom that are inherently discrete. Then there's causal set theory, which takes discreteness as a starting point. This approach treats space-time as a collection of discrete points with causal relationships, which point can influence which other point. Space-time geometry emerges from the network of these causal relationships. If space-time is quantized, what would that mean for physics? For one thing, singularities might not exist. In general relativity, you can have infinite density and infinite curvature at singularities like the Big Bang or the center of black holes. But if space has a minimum size and time has a minimum duration, density can't become infinite. There would be a maximum density, the Planck density, beyond which the classical description breaks down and quantum gravity takes over. This could resolve some of the problems we have with black holes and the Big Bang. Instead of a singularity at the center of a black hole, there might be a region of Planck-scale quantum geometry that we can't describe with classical general relativity. Instead of a singularity at the Big Bang, there might have been a quantum state from which space-time emerged, Quantized spacetime might also have observable consequences. Light of different wavelengths might travel at slightly different speeds if spacetime has discrete structure. Shorter wavelengths might interact with the discreteness differently than longer wavelengths. This effect would be tiny, but it might be detectable for light that's traveled across cosmological distances. We've looked for such effects in observations of gamma-ray bursts, extremely energetic events in distant galaxies. If spacetime were discrete at the Planck scale, photons of different energies should arrive at slightly different times after traveling billions of light-years. So far, we haven't detected any such effect, which puts limits on how discrete spacetime can be. But the absence of evidence isn't evidence of absence. The effects might just be too small to detect with current instruments, or the structure of quantized spacetime might not produce the effects we're looking for. The question of whether spacetime is continuous or discrete remains open. We don't have a confirmed theory of quantum gravity, so we don't know what actually happens at the Planck scale. We're extrapolating from what we know, quantum mechanics and general relativity, and trying to guess what physics might look like when both are important simultaneously. But the very fact that we can ask this question, whether spacetime is fundamental or emergent, continuous or discrete, shows how far we've come from Newton's absolute space and time. Spacetime isn't just the stage where physics happens, it's a physical thing with its own structure, its own dynamics, possibly its own quantum properties. And this brings us to perhaps the deepest mystery. How do quantum mechanics and general relativity fit together? Because right now, they don't. And that incompatibility is at the heart of our incomplete understanding of space-time. Quantum mechanics and general relativity are the two most successful theories in physics. Quantum mechanics describes the behavior of matter and energy at small scales with extraordinary precision. General relativity describes gravity and space-time curvature with equal success, but they're fundamentally incompatible in a way that creates deep puzzles about the nature of space-time. The core tension is this: quantum mechanics is inherently probabilistic. A particle doesn't have a definite position until you measure it. It exists in a superposition of many possible positions simultaneously. When you measure it, the superposition collapses and you get one definite outcome. This measurement process is weird and still not fully understood, but it's fundamental to quantum mechanics. General relativity, on the other hand, is deterministic. Given the distribution of matter and energy at one time, Einstein's equations tell you exactly what the space-time geometry is and how it evolves. There's no probability, no superposition, no measurement-induced collapse. Space-time has a definite geometry at all times. Now try to combine these. Imagine an electron in a superposition of being at position A and position B. According to quantum mechanics, it's really in both positions until measured. But each position would curve space-time slightly differently. The gravitational field is different if the electron is at A versus B. So what's the geometry of space-time? Is it curved, as if the electron is at A, as if it's at B, as if it's at both positions? Or is space-time also in a superposition? If space-time can be in a superposition, what does that even mean? A superposition of different geometries. How do you describe that mathematically? What are the rules for how superposed geometries evolve and interact? These aren't just academic questions. They have practical implications for situations where quantum mechanics and gravity both matter, like the very early universe near the Big Bang, or the interior of black holes, or potentially even in tabletop experiments with quantum sensors. One perspective is that space-time must be quantized too. If matter is quantum mechanical, and matter curves space-time, then space-time itself must have quantum properties. This leads to quantum gravity, the attempt to formulate a quantum theory of space-time itself. But this creates new problems. In quantum field theory, we quantize fields, electromagnetic fields, electron fields, etc., by treating them as made up of quantum particles, photons, electrons. If we quantize space-time, are there gravitons, quantum particles of space-time geometry? How do they interact? What's the quantum state of space-time? Another problem. Quantum field theory works in a fixed space-time background. You have fields living on top of space-time, and they interact according to rules that assume the space-time geometry is fixed and classical. But in quantum gravity, space-time itself is quantum and dynamical. There's no fixed background to work with. You need a theory that doesn't assume space-time exists in advance. A background-independent theory. General relativity is background-independent. It doesn't assume space-time exists beforehand. The geometry and the matter distribution are solved for simultaneously. But quantum field theory is background-dependent. You need to specify the space-time geometry before you can write down the theory. Combining these seems impossible. You need quantum field theory to describe matter, but quantum field theory needs a space-time background. You need general relativity to describe space-time, but general relativity doesn't include quantum mechanics. They each need something the other doesn't provide. Then there's the measurement problem in quantum mechanics itself, which becomes even more problematic when you include gravity. In quantum mechanics, measurement is a special process that collapses the wave function. But what counts as a measurement? What collapses the wave function? Is it interaction with a classical measuring device? Is it decoherence from the environment? Is it something about consciousness? These questions are hard enough without gravity. With gravity, they become absurd. If space-time is quantum, and measurement involves space-time, then what geometry does measurement happen in? How do you even define what a measurement is when the structure of space-time itself is quantum and uncertain? Some physicists think the measurement problem suggests that quantum mechanics needs modification when gravity is included. Maybe superpositions collapse spontaneously when the gravitational energy difference between different states exceeds some threshold. This would be a fundamental change to quantum mechanics, introducing objective collapse driven by gravity. Others think the measurement problem is telling us that our entire framework is wrong. Maybe neither quantum mechanics nor general relativity is fundamental. Maybe both are approximations to some deeper theory that doesn't have these contradictions, a theory where space-time and quantum mechanics emerge from something more basic. This is the frontier of physics. We have two incredibly successful theories that describe different regimes: quantum mechanics for small scales and high energies, general relativity for large scales and strong gravity. But we don't know how to combine them. We don't have a theory of quantum gravity that everyone agrees on, and without such a theory, we can't fully understand space-time. We can't describe what happens at the Big Bang, or inside black holes, or at the Planck scale. We can't answer questions about whether space-time is fundamental or emergent, continuous or discrete, deterministic or probabilistic. The incompatibility between quantum mechanics and general relativity is perhaps the deepest unresolved problem in physics. It's telling us that our understanding of space-time is incomplete. There's something we're missing, something fundamental about the nature of reality that we haven't grasped yet. But recent developments have suggested a surprising connection that might point toward a solution. Quantum entanglement and space-time might be deeply related. Quantum entanglement is one of the strangest phenomena in quantum mechanics. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and thought it showed that quantum mechanics was incomplete. But entanglement is real. It's been verified in countless experiments. If you have two entangled electrons, measuring the spin of one immediately determines the spin of the other, even if they're on opposite sides of the galaxy. The correlation is instantaneous, faster than light could travel between them. This doesn't violate relativity, because you can't use entanglement to send information faster than light. The measurement outcomes are random. You can't control them. You only see the correlation when you compare measurements later, which requires classical communication at or below light speed. Still, entanglement seems to create a connection between distant points in space, a connection that isn't mediated by anything traveling through space-time. It's a relationship that exists independently of distance. In 2013, physicists Juan Maldacena and Leonard Susskind proposed something radical. This non-local connection of entanglement might actually be a wormhole. They called it the ER equal sign, EPR conjecture, connecting Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen pairs, entangled particles. The idea is that when two particles are entangled, they're connected by a wormhole through spacetime. Not a traversable wormhole. You can't send information through it, but a geometric connection nonetheless. The quantum correlation between the particles is reflected in a geometric connection in spacetime. This sounds crazy, but there's mathematical evidence for it. In certain theoretical frameworks, particularly in ADS/CFT correspondence, a connection between gravity theories and quantum field theories, you can show that creating entanglement in a quantum system creates geometric connections in the dual gravity description. If ER equal sign EPR is correct, it suggests something profound. Space-time geometry might emerge from quantum entanglement. The connections and relationships between quantum states might be what creates the structure of space itself. Think about it this way. Space is a network of relationships between points. This point is connected to that point. They're a certain distance apart. Signals can travel between them at certain speeds. What if these relationships emerge from quantum entanglement between the quantum degrees of freedom at those points? In this view, space-time isn't fundamental. Quantum entanglement is fundamental. Space-time is what emerges when you have vast numbers of quantum systems entangled in complex patterns, distance, geometry, even the notion of separate points in space. All of these emerge from the entanglement structure of an underlying quantum state. This is related to ideas about holography and the holographic principle. The holographic principle says that the information content of a region of space is proportional to the area of its boundary, not its volume. This suggests that the three-dimensional space is somehow encoded on a two-dimensional surface. In ADS/CFT correspondence, you can see this explicitly. A quantum field theory living on the boundary of a space is exactly equivalent to a gravity theory living in the bulk of that space. The quantum entanglement in the boundary theory literally creates the geometric structure of the bulk space-time. This has led to proposals that space-time is fundamentally a quantum error-correcting code, that geometry emerges from entanglement entropy, that the Einstein equations themselves are equations for the entanglement structure of quantum states. These ideas are still speculative and not fully developed, but they point toward a radical reconceptualization of space-time. Instead of space-time being a fundamental arena where quantum fields live, space-time emerges from quantum entanglement. Quantum mechanics is more fundamental than geometry. If this is right, it could resolve the tension between quantum mechanics and general relativity. They're not incompatible. One emerges from the other. General relativity describes the emergent space-time geometry created by quantum entanglement. At the Planck scale, where entanglement structure breaks down or becomes quantum, space-time itself breaks down. Singularities are regions where the entanglement structure can't support a smooth geometry. This would also explain why gravity is so weak compared to other forces. The other forces are fundamental. Gravity is emergent. It's a consequence of space-time geometry, which is itself emergent from entanglement. Emergent phenomena are generally weaker and longer range than the fundamental interactions they emerge from. It might also explain dark energy. If space-time emerges from entanglement, then the vacuum energy of space, the energy of empty space itself, might be related to the entanglement structure of the vacuum state. The cosmological constant might be telling us something about the quantum state of the universe on cosmological scales. These are deep, speculative ideas. We don't have experimental evidence for them. We don't have a complete theory. But the connection between entanglement and geometry is real. It's been demonstrated mathematically in specific contexts. Whether it extends to our actual universe is an open question. What's becoming clear is that space-time is far stranger and more subtle than anyone imagined. It's not just a stage where physics happens. It's not even just a dynamic geometric structure. It might be an emergent phenomenon arising from quantum mechanics. The very notion of space and time might be approximate, useful at large scales, but breaking down at the fundamental level. And this brings us full circle to Einstein's original insight. Einstein showed that space and time are not separate, that they're united in space-time, that space-time is curved by matter and energy. This was revolutionary. But a century later, we're realizing that Einstein's space-time might not be the end of the story. It might be an emergent description, extraordinarily accurate at the scales we can measure, but not fundamental. Underneath, there might be something else, a quantum reality where entanglement and information are primary, and space-time is what emerges when you zoom out. We don't know yet. The experimental evidence isn't there. The theoretical framework isn't complete. But the hints are tantalizing, and they suggest that the mystery of space-time, Einstein's idea we still don't understand, is deeper than anyone imagined.